All right, let's get started. So we have 5 talks in this session. And in the first talk, we'll hear about how to make fast context-free language reachability queries. And Chen Han will be giving the talk.
Thanks for the introduction. And this is Chen Han Shi from Institute of Computing Technology, University of Chinese Academy of Sciences. And today I'm going to present our work titled Fast Client-Driven CFL Reachability via Regularization-Based Graph Simplification. And this is a joint work with Dongjie, Haofeng, Jielu, Lianli, and Jingling. Context-free language reachability is a very popular framework for formulating a wide range of program analysis tasks, such as pointer analysis, tensor analysis, and sizing, to name just a few. So to make sure we are on the same page, I will start with an example of available expression analysis. So in this analysis, the client wants to ask whether the expression star x plus 2 at line 9 can reuse the value computed at line 7. So if this is the case, we can do some program optimizations. As you can see, this expression loads a value from variable x, and line 8 stores a value to variable s. So what this client actually needs is the memory alias relationship between star x and star s. And we can do this via CFL reachability. So in this framework, we encode the program as a graph. And in this graph, each node represents a program expression. For example, we have a node s for this variable s. And edges encode pointer semantics. For instance, this assignment statement at line 5 can be translated into an edge from node R to node S labeled by A, and we call this edge an A edge. And we can do similar things for pointer reference and pointer dereference. Lastly, we also need to add some inverse edges, that is, edge labels with an overline. So we have our edge label graph representation. Next, we also need to specify the analysis with a context-free grammar using production rules to express pointer semantics. This CFG context-free, this grammar is a bit complex, so I will just give you an intuitive overview without going into the details. So here, the non-terminal A, uppercase A, denotes direct assignments or indirect assignments. And we also have V value alias, meaning that 2 pointers point to the same address. Lastly, we also have memory alias, denoting that 2 expressions evaluate to an identical memory location. So as can be seen in this production, pointer reference and dereference are properly matched. Let us revisit our motivating example. So we have this source to sink path, and the path string can be obtained via concatenating the edge levels along the path. And we can see that we can derive this path string from the non-terminal M. So we can conclude that this path is M-reachable. And we recall that in this path, the numbers of the by edges and the are properly matched. They denote pointer reference and dereference. So at a high level, in this CFL reachability framework, we kind of have a context-free grammar to encode the analysis, and we also have a graph to express the program semantics. Then we have an algorithm which takes as input the grammar and the graph, and outputs the analysis results, which are also encoded in a graph. So let me explain our paper title a little bit. For the client-driven part, highlights our motivation. That is, clients only need reachability information for certain source-to-sink paths. And based on this observation, we want to make this algorithm to run really fast. This is done by performing graph simplification, which is guided by a CFG regularization. So to formally state the problem, Given two node sets, we source and we think we want to design a pre-analysis to produce a simplified input graph to preserve the reachability solution for all source to sink process, and with a negligible runtime overhead. And we also want to reduce as many useless edges as possible. The challenge here is to maximize the removal of non-contributing edges while ensuring the pre-analysis remains lightweight. So an edge is L contributing if it lies on an L reachable path from a source to a sink. And our solution is to over-approximate contributing edges. So by over-approximation, we typically include some non-contributing edges for efficiency. And so we first use language L prime to over-approximate L. That means L prime includes all the strings generated by L. And under this approximation, we can some kind of relax this reachability. That is L reachable passes are also L prime reachable. And ultimately, we can over-approximate contributing edges. So L contributing edges are also L prime contributing. Our choice is to regularize L via the well-known element transformation techniques, since regular languages are less demanding computationally. For example, we have our regular languages on the right. So what we do here is to preserve L prime contributing edges as an over-approximation. So to revisit our source to sink path again, and we can see that under this new language L prime, we can still derive the path string from M. So, but recall that this path string exhibits some matching behavior. That is, we have even the equal numbers of D bar edges and the edges. Since we use over-approximation, so we have some unwanted passes. This is a case. In this path, we can see that this matching behavior is missing due to regular approximation, because regular language cannot model such behavior. We propose automaton-guided graph simplification. We use a finite automaton, an equivalent representation of regular languages. We exploit their state transition rules to efficiently identify contributing edges. For example, we have our regular language and an FA and the corresponding DFA here. To identify contributing edges, we introduce the notation of configuration train, which are obtained by consuming path strings with FA. So in this train, each item represents a node with one of its reachable states. An edge is contributing if it contributes to a train from source to sink, starting with the initial state, ending with final state. Here is the train for our motivating example. So to this end, we propose an efficient algorithm with linear complexity with respect to the edge count. The key here is realizable states. We kind of intersect the reachable states from sources forward and sinks backward under the DFA guidance. And an edge is contributing if it contributes to the transition between two realizable states. Here we use DFA since it is better than NFA in our case. It has fewer states in practice, though without any theoretical guarantee, and fewer state transitions. Here are the transition sequences for NFA and DFA respectively. As we can see, the sequence for DFA is much shorter. So this brings us to the evaluation part. We have implemented Moye as a pre-analysis with Python 3 and LVM. We evaluate our approach on two clients, point-to analysis for Java and alias analysis for CNC++. So we use standard benchmarks, including Dakapo and Spec, and we compare our approach with a state-of-the-art method, graph folding, or GF for short. Here's the subjects for tool analysis and their corresponding DFA. So in terms of pre-analysis efficiency, in point-to analysis for Java, we can see that our pre-analysis only introduced negligible overhead when compared to the CFL main analysis, while CFL is unscalable for some large benchmarks, as we show here. So this is the case for C++. In terms of graph size reduction, we can see that Moyer achieves reduction rates of more than 60% and 70%, significantly outperforming GF, and their combination can also achieve greater reduction rates. And this also applies to C and C++. So in terms of speedups, our approach achieves 10 times and 15 times for tool analysis respectively, and also outperforms GF, and their combination also achieves greater speedups. And this also applies to memory savings. And we also evaluate our approach on challenging benchmarks. For example, GF, Moyer, and combined can scale up to 3, 5, and 8 more benchmarks. Compare an approach without graph simplification. So we also evaluate our approach in a batch setting in our paper, but in this experiment, Moyer achieves even greater improvements, and more details are in our paper. You are free to reach our paper, see our paper. So to conclude, we have proposed a regularization-based graph simplification to pinpoint contributing edges and design a linear pre-analysis. So future work, we can exploit tighter approximation by exploiting the subject characteristics in program analysis. And I'm also seeking postdoc positions starting next year. Thank you for your attention. And now I'm happy to take any questions.
Maybe I'll start with a question. Is your analysis inter-procedural or intra-procedural?
It's only intra-procedural because for SFG, it can only models field sensitivity, but it cannot model contests and fields at the same time.
So can you extend your approach to handle function calls eventually?
Yeah, I think so. So we can do some kind of like function cloning to do this. Yeah.
Anybody? So I'm curious. At what point the simplification is worth it? If I have a super simple query, if it's already regular, then your tool wouldn't help me. Like some queries, like it seems like your tool helps if the query is complex, or if the graph is complex, or both.
When it works, when the graph are complex, yeah.
Okay, so even if my query is simple, but if the graph is complex, yeah, your tool still is worth it.
Yeah. So we have fewer sources and things. Our approach will achieve greater reduction rates. Yeah.
So maybe let me ask you one more question. So have you looked at in security we use this CPG code property graph?
Oh, like Yong or.
That's the initial work. Right now there's CPG for other languages too. We worked on JavaScript, for example. So when we do security analysis, you do code injection attack. That's a taint path we're querying. Prototype pollution, you have 2 taint paths and some other ordering. Do you see your tool can be applied in like CPG query, speed them up also? Do you have a sense of where we at?
it may be an interesting topic to explore in the future, and I think so. Yeah.
All right.
Thank you.
All right, for our second talk, we'll hear about how to bring types to graph query languages, and Wen Jiaye will be giving the talk. Go ahead.
Thank you for the introduction. Hello, everyone. I'm Wen Jiaye. Today, I'm going to talk about the work Flexible and Expressive Type Pass Pattern for GQL. It's a joint work with Matthias, Thomas, Bruno, Manuel, and Domago. The name, So we know graph database has become an important data management technology across various domains, including biology, sociology, finance, and also journalism. And there are query languages for querying graph, like Neo4j, NGQL, and GraphQL. Also, the newly proposed GQL. So what is GQL? GQL is a new ISO standard for graph language that's being developed by the same teams that develop SQL. So just to quick explain what GQL is, so in a graph you can have node, and a node has an identifier. It has a set of labels, and it has some properties. For instance, here we have a node account. The ID is N1, the label are just account, and the property is that its owner is arena and its block is false. So it has two properties. Then we have edges that related to nodes. It has the same structure as a node. So it has an identifier, it has a label, it has properties, and also it has a direction. And the edge could be either directed or undirected. So, for instance, here we have a graph with two edges. Below, we have a pass query, which is a query over the graph. So it's kind of a regular expression. So you are saying we want to match all the nodes and store the results in X. That is connected with an edge. Store the resulting Z that has an edge, which has a label transfer. And also, the property amount is bigger than 1 million. And the edge is point to another node, such that the property is block is true, and store the result in variable Y. So you just match. Then you could concatenate each of these components and get the possible results. So the result in this case is the path N2, E2, and N3. And you can have more if the graph is bigger. And in X, we store N2, which is the source node. And in Y, we store N3, which is the target node. And in Z, we store E2, which is the edge. And there are some issues in graph query languages. For example, query can fail at runtime or return empty result without prior warning. And most graph queries in large number contain large number of joins to traverse the graph, to traverse the relationship. Then if the query produces an empty result, it will cause unnecessary computations, and it will hurt the efficient query evaluation. And the GQL ISO standard defines types for data. It lacks a formal type system for validating queries. Also, the GQL ISO standard is written in a mix of prose and pseudocode, make it difficult to interpret, so it requires a formalization. Now, let's look at some example to know exactly how a query can go wrong. For instance, you could write a query like the first one, where you have an incompatible shape. So you're trying to store both a node and an edge in the same variable. And according to the ISO, this is syntactic invalid. You could have also have incompatible properties. So for instance, you could say the property is block of a node is Boolean, and also it's a string at the same time. Then if you do the pass query, which is like a self-references, and then a node that goes from the source and the target is the same node. So this is fine, because it's going to test the property is both a Boolean, or if it's both a Boolean and a string, then the result is going to always empty, because there's no node that satisfies these two things. Also, you can have the non-existent attributes. This query gives us empty, and the problem was that this attribute was that we have a typo in the attribute. But and the ISO doesn't say exactly what we should do in this case. Sometimes it says you can crash or return empty. But it definitely depends on the schema. If we have this amount in a schema, then we will have result. And the other thing could go wrong is wrong usage of attributes. For instance, a Boolean as a number, and again, the behavior expected by the specification is, it depends. It could crash or it may return empty. And also, you can have error of unbound variable. And here, for instance, you are trying to reference a variable that is not in the scope. So this will give you a stuck execution. So in summary, if you have a pass query, you can have several results. One of them is that you have a result, you return something, and it's non-empty, which is happy because it's the best cases. So the other kind of result is an empty result, which is unexpected. And this empty result could be because there are some non-relevant data or due to, for instance, type inconsistency. And the other kind of result is you will get a fatal error or you stuck. And when you evaluation. So our goal for this type system is to provide a type system. Our goal for our work is to provide a type system that under approximate queries that are going to definitely be empty. So you should give warning for program that will definitely return an empty result, and over approximate the stuck evaluation. So you may want to conservatively reject program that potentially get stuck or abort during execution. And also, we want this system to be flexible. Then it would allow us to incorporate this gradually. For instance, starting with a schema, but with no type. And gradually, we can add types into it. Then we can add type annotation to the schema and get more feedback. To achieve this goal, we introduce the flexible path pattern calculus. It's FPPC, and it's a formal model of the path pattern language of GQL. We extend with new syntax by filtering with property types. And to achieve flexibility, we draw inspiration from gradual typing. We extend both the schema and the path pattern language with imprecise type information by introducing an unknown type. And the unknown type can represent labels or properties. So an overview of the system is like this. So we start from a partial schema, which may have some unknown information in it. And it's like describe what is the type of the node and what's the type of the edge that you may find. Then you have a query. And then we have a type system that either says this is an error because this could fail at one time, or it will give you a result, which is a path types and a context. And the path type basically is the type of the path that you are going to return. And the context is the type of every variable that you are binding. And taking those two things, path types and context, we could say that we could say to the user if the query is going to be empty or not. When we say but inside this one, we say if to match with our goals, we say if there is an error, then it's an over approximation, and if we say empty, then it's under approximation. And also, we have the flexibility because we can have the partial schema. And the type system of our FPPC can detect all errors for a previous example. For example, the first example, the incompatible shapes is EO type because the meet between a node type and an edge type is not defined. Then for the second example, the incompatible properties raise an empty result because the meet between bool and string is bottom. Then non-existent attribute is EO type because the attribute could not be found in the schema. Of course, it depends on the schema. If we have this typo amount, then it's going to be well typed. Then another one is the long usage attribute where raised and empty because type error in the conditional tense is propagated to the patterns. Then the final example is ill type, since X is absent from the context. Then to validate the formal development of our FPPC and support interactive experiment with type graph queries, we implement a Python prototype. And this design supports informative feedback and allows the analysis of partial valid queries. For instance, consider the pattern. This query is syntactic valid. Both contain a type inconsistency or a reference to an unbound variable. And the type checker will give us the diagnostics, says there is warning message about the type inconsistency, and there is a variable cannot found error. Then we prove some properties, for example, type safety of the type system, and it guarantees that well-typed path queries cannot get stuck or produce runtime error. And another important property is empty properties. It ensures that if a query type checks, but its type is flagged as empty, then it will definitely return an empty result due to type inconsistency. And we also prove the important properties in gradual typing, gradual guarantee, and it ensures that if we're removing some type annotation, then it will not introduce either type or runtime errors. So in summary, this work makes these contributions. We present the FPPC, and it's a formal calculus for GQL, and extends with the ISO standard with property-based filtering and gradual types. And we extend the past pattern language with type property expression and now allowing nodes and edges to be filtered based on both labels and property types. And we prove the empty property, type safety, and gradual guarantee. And also, we provide a prototype implementation of FPPC. And our current prototype, for the future work, because our current prototype focuses on a core fragment of GQL, so for future work, we are supposed to, we may need to support the full range of GQL queries. And we could extend features such as aggregation and negation enable predicate. And a possible solution is a set theoretic approach. Then we could explore optimization for query evaluation under this typing enhancement. Also, we can do further refinement to the interaction between schema evaluation and gradual typing in graph database. Due to the time limit, I just provide an overview of this work. You can scan the code if you want to know the full details of our work. Thank you.
You'll start first. How do you evaluate your work?
Sorry?
How do you evaluate your system, your type system?
Evaluate our type system.
Do you have case study that you run?
Because GQL is quite new, so there is no graph query database. So we haven't do this kind of case study. Yeah.
Hi. Hello, Max New, University of Michigan. So you have a runtime monitoring kind of system to run queries that have partial type information, right? So a big problem with gradual typing for higher order languages is that this can get very expensive. So is it relatively cheap for this kind of query language, or do you still run into performance issues with that?
I think because of the performance issue of gradual typing, I think if we support like higher order function, we will also have these issues. But we can improve the performance of graph query is that you can address empty. So the focus to improve the performance is not is about we can address empty result, empty warning.
Right. But I'm saying you don't have higher order functions in
No,
this
we
setting,
don't have
right?
higher
so
order
it might be that it turns out to be acceptable over
Yeah.
Okay.
So we don't have a higher order function. So maybe we don't need to consider the performance issue. But if we have a higher order function, I think that would be an issue.
Okay.
Yeah.
Thank you.
I can take this. All right. All right, so this is the first time I'm sharing my own paper, so you all have to come up with questions. So now Landu will talk about our work on reasoning about under-approximation.
Hi everyone, my name is Lang Liu. I'm a PhD student at Illinois Tech. Yes, this is the joint work with my advisor Fazanai Li Ming from CMU, Gabriel and Mark from SEI. Nowadays, formal methods are drawing attention because critical system demands strong guarantees. It results in many verified software like CL4 and the verified TLS implementation. If all the components in the system are verified, then we say the whole system is verified. But for large software like Chrome, it has more than 30 million lines of code. So fully verified seems unrealistic. So instead, large systems usually use many tested components. For example, an operating system may combine the verified CL4 with many tested device drivers, while a browser may combine the verified TLS with many tested components. The question is, can we compose those tested behaviors and then declare the system satisfies all of them? The example on the next slide shows the answer is no. In this example, say we are testing a window. The handyman number 1 comes on a sunny day above freezing. He opens and closes the window. No screeching noise, perfect. Then handyman number 2 comes on a cold morning below freezing. He checks for condensation. The glass is clear, no fog, no problem. We need to notice that those behaviors are only tested to work under some conditions, which is an under-approximation. So we call them under-approximation analysis. Comparatively, verification checks all possible conditions, which is an over-approximation. Here, each testing looks great, but can we compose them and say the window works well in general? We need to notice that the intersection of the two conditions yields an empty set. So the empty set means the two testing results never shown to hold at the same time. So the composition does not make sense. The window may still start squeaking or fogging again. Here we show the problem of composing testing analysis. Composing testing with verification adds extra complexity. Our goal is to design logical foundation to reason about the composition of heterogeneous analysis. I will show you how to formalize our idea with another example. By quantifying under-approximation with another example. The example is a space launch vehicle called Ariane 5. It reused two components from its predecessors, Ariane 4. The IRS, inertial reference system, and the OBC onboard computer. OBC has two variables as its internal resources, LT, the launch trajectory, and temp, the internal temperature. Those two components work together. OBC calculates and sends HV, the horizontal velocity, to IRS. IRS then calculates align, the alignment data, and then send it out. These two components were tested to work well in Ariane 4. However, with assuming those testing results from Ariane 4 and directly reusing those components, the first flight of Ariane 5 failed. Ariane 5 has a different launch trajectory that results in a much higher HV. The HV cannot be stored in a 16-bit site integer in IRS. An exception was sent out after an operand error happened in IRS. The exception was not handled properly, finally leading to the failure. The lesson is we should never treat under-approximation analysis as if they were analyzed under all possible conditions. To prevent situations like this, we propose to quantify the level of under-approximation via a modality. It ranges over the component's internal resource values. For example, here, the analysis on OBC in Ariane 4 only consider the cases where the internal value of LT is less than some V0. So we attach this modality to the guarantee of this analysis. It shows that this guarantee does not work for RN5 because RN5 has the different LT that is not covered by the test cases here. More importantly, this modality enables us to soundly compose differently analyzed components. I will show you how to formalize our idea and what the main challenges are with two analyses from RN4. In the first analysis, it establishes that the HV is positive and within 16 bits and the right side of the turnstile. And the left, it makes two assumptions on the output HV. Let's assume the HV is tested to be positive when temp is greater than 0 with any LT. HV is also tested to be within 16 bits when LT is less than V0 with any temp. We quantify these two assumptions with two sets. They are the modalities we mentioned earlier. They describe the condition under which those assumptions are tested to work, those behaviors. So we call them test levels. I think we all agree that the guarantee only holds for the intersection of the two sets. We call the intersection T1. In this way, test level quantifies the level of underapproximation. And to make it more interesting, I will show you another analysis that works on disjoint resources. For that, we add an additional component, SNS, the sensor. It sends ENV, the environmental data, to IRS. This analysis is on the component IRS. It makes two assumptions on its two inputs. First, there is an input ENV, no matter what its value is. Second, the input HV is positive and within 16 bits. Then this analysis declares that the output align will not be an exception. Assume assumption 1 is established via a verification, so it works for all the possible internal resource values of SNS. We note this as max SNS, which is the test level for assumption 1. From the last slide, we know the test level for assumption 2 is T1. So what's the test level for the guarantee here? This time, an intersection does not make sense anymore because max SNS and T1 apply to disjoint resources. So instead, we use a disjoint union to compose them. However, this is still not enough. From the system diagram, we can see the value of align also depends on IRS. So we also need to consider the internal value of the test level for the internal value of IRS. Assuming this analysis is a verification, so again, we note this as max IRS. The test level for the guarantee turns out to be the disjoint union of max SNS, T1, and max IRS. Now, we have observed two ways to put assumptions together. In the first judgment, both assumptions are describing behaviors that rely on resources of the same component, the blue OBC. But in the second judgment, the two assumptions are describing behaviors that rely on disjoint resources. But despite these two different interpretations, we put them together using the same separator. We need to find a way to unify these two interpretations. To give you a better analogy, the first interpretation is similar to the regular conjunction in separation logic. It talks about the same heap. But the second interpretation is similar to the separating conjunction. It works with two disjoint heaps. It turns out there is a nice logical foundation that can help with this unification. It's called the logical bunch implication. I will give you some background and show how we build our system on top of it. The logical bunch implication was proposed by O'Hearn and Pym in 1999. It merges intuitionistic logic and multiplicative intuitionistic linear logic. In BI, formula borrows connectives from both sides. Its context has two separators. As shown in the example, the semicolon context with the same resources, while comma for disjoint resources. We say we use test level to quantify the level of underapproximation. To achieve that, we need an additional layer on BI. So we extend the atomic formula BI to capture component behaviors. Now it is the predicate PX, where X is the message along channel C. The predicate is quantified by a test level T. It describes the condition under which this predicate holds. Finally, we annotate a judgment with its corresponding analysis name A. We also require a judgment to be well-formed. It means that the context gamma and the guarantee B should describe behaviors that are based on the same set of resources. With BI in mind, let's look back to our two naive judgments. For separators, we really need semicolon for the first judgment and a comma for the second judgment. The second judgment is not well formed, so we add an additional unit component to the context. It represents any behavior for the pink IRS component. Test level quantifies the level of an approximation, and it continues to do so after analysis computation. For example, here, the test level for the guarantee of the second judgment shows that the guarantee only holds when the internal resource of the blue OBC satisfies T1, which requires that LT to be less than V0. This only holds for area 4, but not area 5. It explains why area 5 failed after composing this reused OBC with other components. Now, with those property structure judgment, our next step is to define its meaning with Kripke style semantics. First, we define the possible words as a set of action traces. With standard reduction and computation, it forms a pre-ordered commutative monoid. Then we define our Kripke style semantics based on whether a trace satisfies the behavior described by the gamma or the formula B. For the detail of the semantics, please look at our paper. Based on the semantics, a judgment gamma gives us B can be interpreted as if a trace satisfies the behavior described by the gamma, then it should also satisfy the behavior described by the guarantee B. Now we know how to structure a judgment, define its meaning. Next, we define a set of rules to reason about those judgments. The rule set is a Ginton-style sequent calculus called label BI. For the rule details, please refer to our paper. To show that our development is sound, is reasonable, we build two important properties. First, label BI enjoys K-elimination. Second, label BI is sound with respect to our Kripke semantics. Those two properties are helpful in our framework composing different analyses. The framework works like this. Given the system structure, a set of analyses, and the goal, a proof search for the goal can be processed with the label BI rules. It takes all the analyses as axioms and is based on the K-elimination algorithm. Similar to other calculi based on Bunch implication, the proof search algorithm is not terminating, so we make it interactive, allowing hints from users. If the derivation does not exist, the output is an error. Otherwise, the proof derivation is generated. In that case, our soundness theorem guarantees the goal derived within the derivation is meaningful. We also build an implementation to automate this process. It's written in OOPSLA. This is a summary of our contributions I will not repeat again. There are also other work that consider under approximation, for example, incorrectness logic. However, it composes the evidence for the reachability of bad states, aiming to find bugs, while label BI works on the reachability of good states. As for future work, we plan to fully automate the proof search by designing a terminating calculus for label BI, possibly with ideas from G4 IP. And now label BI works on systems that in a bank structure. We also plan to support a system beyond this by incorporating inductive reasoning principle with test level invariant. The idea is very similar to the resource invariant in separation logic. That concludes my presentation today. Thanks.
Thank you for talk. I think the intention that treating separately with same resource and different resources, not only for under approximative analysis. So I wonder why you stick with under approximate analysis.
Gotcha. Thanks for the question. I should clarify that. Then because you want to say like over approximate analysis also should be composable, right? Yeah, they are composable. There are some previous work that, like relay guarantee reasoning that can support you to compose over approximate analysis. So our novelty is that we included this under approximation part to make it composable. Yeah. Does that answer your question?
Maybe we can take this offline.
Okay.
Yeah. All right, switch
Yeah.
Yeah, we're slightly behind. I thank the speaker again. Okay. This last talk before lunch, and Professor Max New will tell us about stacks and monads.
Hi, yeah, I'm Max, University of Michigan, and this is my joint work with my PhD student, Yuchen, and former undergrad, Runza, who's starting at Indiana this semester. Okay, so this talk is about implementation of effects in our programming languages. So things like exceptions, mutable state, and continuation effects, right? And if I ask you, okay, how am I going to program with these effects in my programming language? Well, it depends on the setting, right? So on the one hand, we have how we abstract over effects in our high-level programming languages, things like Haskell, Scala, OCaml, right? And for that, we know that due to the great work of Moji and Wadler in the 80s and 90s, we can use monads, right? So what is a monad, right? Monad takes a type A and gives you a type TA that we think of as the type of effectful programs that return A values. And the monad interface gives you the most basic operations that such an effect should support. So we can embed pure values using return, and we can sequence with a kind of let binding, which we use with do notation. Okay? And then we can instantiate all this with different effect implementations within our language to kind of virtualize these effects, to add them to a language that doesn't already have them. Okay? So, on the other hand, ICFP is over, and now we're at OOPSLA. Okay? So, so rather, we'd probably say, I'm going to just have those effects in my programming language already, and I'm going to implement those effects in my compiler. Right? So what does that look like? Well, it doesn't look that different, but it's a little lower level. Right? So as an example, let's look at 3 different ways that we can implement exceptions in the compiler for a language that has them. Right? So on the one hand, we could do something very similar to what we might do with the either monad, which is we have a continuation which says either I'm a successful value A or I'm an error value E. Right? And then I'll have the continuation, the caller stack frames below that. Okay? On the other hand, that's not actually very efficient. There's too much branching on these data values, so a more efficient one is to have 2 different continuations, one for success, one for exceptions, and then I don't have to match on the result. Okay? And then even we have more complicated things like the way we have exceptions in C++, where we have markers on the stack to determine which exception handler to run. And when I raise the exception, I actually have to traverse the entire stack. I need to know how the entire stack is structured in order to implement this, right? So the question I have is, that we address in this work is, what's the relationship between these 2 problems, right? Or to these 2 approaches, right? So on the one hand, we know that we can abstract effects in high-level languages, virtualize effects, using monads, but when we compile them, we have these more low-level ideas of stack manipulation, and we're designing the structure of the stacks. So the question that we address is, what fills in the blank here, okay? And the solution we have is what we call a relative monad. Okay, so contributions of our paper is we adapt this existing category theoretic notion of a relative monad to a call by push value language to talk about abstraction over low-level effects. And then we introduce a kind of extension of do notation for those relative monads. And as an application of that, we show that unlike ordinary monads, we can automatically derive relative monad transformers, so we can build up more complex effectful languages from small components. Okay, so first let's talk about the formal setting that we use, which is called call by push value. And for the purposes of this talk, I like to just think of call by push value as a domain-specific language for working with stack machines. Okay, so call by push value introduces a kind distinction for different types. So on the one hand, we have value types, which are the kind of types we're used to in call by value languages. So that's basic data types, tuples, tagged unions, and closures. And recursive ones, we have recursive data types like our favorite linked lists. And on the other side, we have the computation types. And the way I like to think of these is these are compositionally describing the structure of the runtime stack. So we have a function type, which we think of as describing arguments passed on the stack. We have products, which we think of as encoding destructor tags that are placed onto the stack. The returning type A, which is the continuations that are implemented on the stack, and we have polymorphism as well. And the recursive version of this is we have co-data types. So for example, we can implement a stack-based implementation of a multi-argument function this way. Okay? So how would you do it, right? If you were just a programmer working in call by push value, what would you come up with for monads? You wouldn't come up with the usual notion. Okay? And the reason is that the notion of monad you would naturally come up with isn't a monad because it changes the kind of the types. So an ordinary monad takes a value type and it gives you the same kind of type out. It also gives you a value type, right? Which says that it's a first class value in the system. But when you work in this lower level setting, it changes the kind. It says I take in a value type and I return to you the type of the stacks for computations that perform the effects, right? And so if we're thinking about these computation types as a stack, I can directly express these kind of stack implementation strategies that we saw before. Okay? And this is not a monad because it's not even an endofunctor. And fortunately, there was a paper, monads need not be endofunctors. And it turned out that this implementation that we came up with in call by push value exactly fit into this relative monad setting. Okay, so what does the interface look like, right? We have a TA and it changes the kind. Well, the great thing is it's exactly the same, okay? Exactly the same interface, we just have return and bind. The only difference here is that the TA is a computation type rather than a value type, right? So it very easily generalizes everything that we had before, and we can implement all of our favorite monads that we have in high-level languages. But what else can we do? We can also go and implement these low-level view of these exception monads. So the first example here, the one from Haskell, we only need to modify it by introducing the fact that this actually returns a value of A plus E rather than just being A plus E. On the other hand, we can use a kind of church encoding to express these multi-continuation implementations. So we take in two continuations, and here the important part is that this R that we're quantifying over is itself actually one of these computation types and not a value type. And it's a bit hard to read, but we can use the recursive code data types to express these complex stack structures, and you can actually implement the stack walking and finding the correct exception handler just as a normal recursive stack manipulating function. Okay, so that's relative monad. So what then did we do with it? So the most familiar thing to do with monads is we get a nice embedded programming language, which is the do notation. Okay, so in a high-level language, and this goes back to the very original paper from Eugenio Moji on monads. He proved a theorem which said, if I have a monad on a model of pure lambda calculus, I get a model of call by value lambda calculus. And that corresponds to a syntactic translation, which is I can embed a call by value programming language, I can translate it into a pure programming language if I have a monad. And this is really just desugaring the do notation. Okay, so what does this look like in call by push value? Well, we get something even better. Okay, so unlike the previous case where we're translating from a pure from an effectful language into a pure language, the difference in call by push value is we actually are translating from call by push value to itself. So given a monad, a relative monad in call by push value, we can do a generalized do notation translation that we call monadic blocks. And you can even iterate this and combine effects together in this way. And so we have a corresponding generalization of this theorem that we call the fundamental theorem of call by push value relative monads. And the details of that are all in the paper. Okay, and so it's a fairly straightforward generalization of do notation, but we have to do some type-directed stuff. But other than that, it looks very much like a kind of do notation you see. You map from the do's to binds of your monad. But you also need to do something for all the things that are not just returning values. Okay, and we call it the algebra translation. Okay, and then as a last example, what do we do with this monadic blocks? Well, we're actually able to automatically derive relative monad transformers. Okay, so what are monad transformers? Well, these are a common tool in high-level language for constructing complicated monads from smaller components. Right? And a monad transformer takes in a monad and it spits out another monad that we think of as adding some new effects. Right? And so by composing these together, we can get complicated monads. Right? And in high-level languages like Haskell, we know that given a monad transformer, you can apply it to the identity monad to get out an ordinary monad. But the other process is not automatic. It takes some ingenuity to figure out what that monad transformer should be, and it turns out that not every monad even has a corresponding monad transformer. Okay? But we saw that this self-translation that we get in the algebra translation did give us a way to combine effects together. And so it turns out that actually relative monads compose for totally free, and I want to give some intuition for why that is. So let's take a look at a state monad. So a stack for a state monad, let's say we store the state at the top of the stack, right? And what happens is we always, in call by push value, have to have a tail of the stack that's owned by the caller, right? That we're not allowed to touch. And the idea is that this fact that we're polymorphic over the tail of the stack is exactly what lets us compose, because we can store our other effects higher up on the stack that we're polymorphic with respect to. Okay, so if that caller happened to be an exception monad, we would get for totally free a combination of state and exception effects. Okay, so relative monads in a sense are always polymorphic over this tail of the stack, and that's why we get this compositionality for free intuitively. Formally, the way we can do it is to use our algebra translation. So what we can do is we can take our implementation of one monad and apply it to the algebra translation for another monad, and we get out the transformed monad. And so if you do this with an abstract input monad, you get out the monad transformer. And so this is a completely automatic process. Yeah. Okay, so there's a lot more details in the paper, including laws of relative monads and formal definition of the algebras and the algebra translation, and a proof that the resulting monad transformers are law-abiding as well, in addition to detailed descriptions of various monad examples and how they adapt to call by push value. All of this is implemented in our research language based on polymorphic call by push value that we call Zydeco, and the artifact is available for that. As far as future work, currently Zydeco is not compiled. We have a stack machine-based interpreter, and so we have stacks we can look at, but what we really would like to do is to implement these efficiently and see if we can use techniques like this one to get performant and correct compilers a la carte. And as an additional, when you do any category theory, you have to think about the dual setting, and so I'm very curious about what a relative comonad construction might look like for a language as well. Okay, that's my talk. Our three main contributions: we adapt relative monads to the call by push value setting, so we get a lower level view of effects. We introduce the monadic blocks to generalize do notation, and we use that to derive relative monad transformers for totally free. Thank you.
Thanks, Max. This seems great, but you didn't talk about the limitations. How is it to program with your language? Are there any sort of pain points you've encountered so far?
So you just mean programming in call by push value?
Yeah.
As a programmer?
'Cause-
Yeah, certainly. So it's very similar to working in CPS, I would say. So I'd say it's a fairly low-level programming language. So I'm more thinking of it as something you would use as a target language, but I know I've also gotten pretty good at programming.
What would you imagine having as your source language then?
Oh, well, you could have a call by value language to start with. You can just have off-the-shelf call by value, call by name. But I do think there are features that are informed by this call by push value structure that we could maybe add to the source languages.
I'm specifically thinking, can you benefit from the fact that you have this composability of relative monads at the level of the source language?
I don't have concrete proposals, but I think I would hope so, yes.
Okay, thanks.
Hi, very nice talk. I wondered, is it allowed for the monad operations to be internally use effects of another monad in this language?
You mean when we use this monadic blocks?
Mm-hmm.
Yeah, so not for free. What you get for free is anything that's closed you can lift like this. But you can basically, we have some syntax sugar that we've proposed. And basically you can parameterize the block by those operations. So it's not very nice to use right now, but you can do it. And we think with some good language design, it could be more ergonomic.
Thanks.
Hi. Could you go to slide 9, please?
Sure.
No. Oh, yes. Here. Beautiful.
Mm-hmm.
On the left-hand side, you have a plus and times, right? That's
yes.
great. And on the right-hand side, you have ampersand, which is width. What about par?
So the duality here is the plus corresponds to the width and the times corresponds to the arrow.
And a more symmetric par, could you speculate what that would mean in terms of stacks?
No.
Okay.
So the thing I'll say about this is it's very important that our computation types are second class in this system, which means that we can implement these as a mutably updated stack in place. Classical stuff, classical linear logic stuff, I don't know.
Thanks all the speakers in this session, and it's lunchtime.
session. Genuine will talk to us about invalidation safety.
So hello everyone. Today I'm going to introduce a type and effect system that can track permanent and temporary invalidation. So let's start with this motivating example. So our system is region-based, so that means that you can have some local regions, and after we leave the lexical scope of a region, then everything on this region will be released. So we use this expression, let region in, to allocate a new region, and it will bind the region handler to the variable R1. And later, we can have some data on this region. We call buffer.make of R1. Then we have a buffer on region R1, and we can put some numbers into it. And then we can also have a nested region. We call it R2. And later, we just call buffer.copy of R2 and XS. It will allocate a new buffer on region R2 and copy all elements from XS to YS. And finally, we call iter of XS. It will create an iterator on the buffer XS and passes it to the parameter function here. And inside the function body, we call clear of YS. So this program is fine because XS and the YS are pointing to different buffers on different regions, even though the numbers inside these buffers are different, are the same. However, if we forget to call the copy function correctly, and instead we assign XS to YS directly, then we will get into trouble, because now XS and YS are pointing to the same memory location. So if we have the clear of YS in the same place, then we will get into trouble, because it will remove all the data here, and it will break the structure of the buffer, and we will get a runtime error, or even worse, we will get undefined behaviors. So we must reject this program. There are many systems that can handle these cases, but many of them are based on linearity or uniqueness, which puts huge restrictions on programmers. So for example, here we have a lambda function, which executes two parameter functions one by one. And we have two lambda functions here. They capture the same mutable cell and update it inside their bodies. This program is fine, but in a linear type system, it will be rejected because we cannot have two mutable borrows simultaneously. And we also want a powerful type inference. That means that we want fewer type annotations, and we want to support implicit generalization. So for example, we want to remove the type parameter and remove the types for all arguments. So our solution is based on Boolean algebraic subtyping and the higher ranked polymorphism. So we combine the subtype constraint solving and the bidirectional type checking. So in Boolean algebraic subtyping, we have type constructors, union, intersection, and the negation. So for example, type inf is positive infinity or negative infinity. So here, positive infinity and the negative infinities are single types and then have corresponding values. And for real numbers are numbers that are not NaN and not inf. And we use the effect system. So we use this notation to say that a term E has type T, and it will raise an effect phi. And for a function, we say that this f consumes a type S and produce an T. And during the execution, the function body will raise an effect phi. So we put the effect inside this bracket. And if a term is pure, or say it has no effects, then the effect type will be bottom, the subtype of all types. And like other effects and region system, we can guarantee the permanent invalidation safety. That means that all the downlink references are unusable. If something belonging to a region is leaked outside, then all the operations on these objects is invalid. And we can also have disjointness reasoning for effects. So we say two effects, phi1 and phi2, are separated from each other if and only if the intersection of phi1 and phi2 is less than bottom. And we also claim that subtyping is important because we want to avoid poisoning problem. That means that if we have multiple subterms, their effect will not pollute each other. And we also want to avoid unnecessary effect coercion. And it also allows us to have fewer type parameters and smoother experiences. And we already introduced what is permanent invalidation. So what is temporary invalidation? It is similar. So we have reference, some references will become unusable temporarily, and later they will become valid again. So let's see this example. So we have a freeze function, which will suspend all the operations on the given region, which has type region of R, and and then executes the parameter function here. So notice that this parameter function has effect E, which is for quantified here. That means that we can have arbitrary operations we want. But we have this and not R, which means that this E should not involve R, and inside this lambda function, we should not touch the region we suspend here. And we can have more advanced use cases, which may require higher rank polymorphism. We will see later. And let's go back to this motivating example. So when we allocate a new region, we also allocate a new fresh abstract type variable. So this variable R1 is rigid. That means that we cannot make any assumption on this type variable. And similarly, we have another abstract type variable alpha2 for the region R2. And we also have this evidence, the intersection of alpha1 and alpha2 is less than bottom, to say that, okay, R1 and R2 are two different regions. And for all elements allocated on a given region, they will also carry this type variable. So for example, YS has type buffer of int and alpha2. So int indicates the type of elements we store inside this buffer, and alpha2 indicates where this buffer is allocated. And for the iterator, IT, inside this lambda scope, it has type iter of int and gamma. So int is similar, and because the iterator is also mutable, so we also need to track where this iterator is allocated. So we have this type variable gamma. However, we do not know where this iterator is allocated, because it is allocated by the iter function, and from the perspective of users, we do not know. So this lambda function must have ability to handle iterators from arbitrary regions. So this gamma must be for quantified in this scope. And finally, if we have operations on a region, we will also use the abstract variable for the effects. So for example, the clear of YS, it returns nothing, so the type is unit, and it has effects alpha2 because we are manipulating region R2. And to guarantee the temporary invalidation safety, we must satisfy this subtype constraint. The left-hand side is the effect of the function body, alpha2 here. And the right-hand side is either gamma. That means that we can freely use the iterator inside the function body, and a fresh type effect variable phi that is not alpha1. That means that when we're iterating over the xs, we cannot touch the corresponding region. So we will also output this phi for the effects of the whole application. However, if we forget to call the copy function, then this time YS will have type buffer of int and alpha1 because it's now pointing to a buffer allocated in region R1, and the clear of YS will have effect alpha1. And this subtype constraint will fail because alpha1 is not something that's not alpha1. So we will reject this program correctly. And let's try to make this example a bit more complicated. We keep this piece of code. We have a nested region, R2, and we create another buffer on this region, and we try to iterate over another buffer, XS, and during the iteration, we call the clear of YS. But this time, let's put this piece of code inside the function body. So now XS is an argument buffer. So the question is how to type check this function definition, because now we don't know what outer regions are, and we cannot have the evidence like what we did previously. And this function f must be available to use in arbitrary environments with arbitrary outer unknown regions. So the solution is to introduce our outer variable. So we call it omega, and it is for all quantified when we have this polymorphic function f. And this omega indicates all the unknown outer regions. So for the xs, it has type buffer of int and beta, where beta is less than omega, to say that this buffer is allocated in some outer unknown regions. And for R2, we also have this evidence. the intersection of alpha 2 and omega is less than bottom to say that this region is different from all outer unknown regions. And if we use fx inside this context, where we have two outer regions, R0 and R1, and they have type region of alpha 0 and the region of alpha 1, respectively, and we have this buffer, xs, which is allocated inside region alpha 1. And if we call this function inside this context, we will substitute all the omega by the union of all abstract type variables for regions. So for example, here, we need to instantiate beta with alpha 1, and we'll also have alpha 1 is less than the union of alpha 0 and alpha 1. And similarly, we'll do the substitution for this evidence. And finally, f of xs returns nothing, and the effect is alpha 1 because we are trying to iterate over this buffer. And finally, a quick summary of our contributions. So the key design of our system is a combination of Boolean algebraic subtyping and high-ranked polymorphism. So, and we introduce the outer variables to correctly abstract the unknown outer regions. And we can support various extensions like scope-safe metaprogramming and exception handlers without changing the core type system. And that's all of my presentation. Thank you for listening.
All right, we'll take some questions.
Thank you for the talk. Could you go back to the place where you introduced the iterator for the first time with the new region, the gamma? I was curious about this constraint because you said that you had one example. Thank you. You had one example which was satisfied, this is fine. Yep. And I didn't understand this because you said that, well, gamma is for all quantified from the iterator. And now you have a constraint that gamma is, you have a subtyping constraint here. How is this satisfied here?
Yeah, so basically the right-hand side is a union type. So basically you need to satisfy either left-hand side or right-hand side. Oh, so alpha 2 here is definitely not gamma because gamma is too abstract. So it must satisfy the right-hand side, the phi and not alpha 1. So if we have alpha 1 is less than not alpha 1, then we will get into trouble. So if we already have this alpha 2 is less than not alpha 1, then we will have, then this is equivalent to the evidence we have here, so it can be solved without any problems. And this phi is a flexible type variable. Then later we will see that we can use alpha 2 to constrain this phi, and later we use this phi to describe the effect of the whole application.
Okay, thank you very much.
Yeah, thank you.
Hi, thank you for the talk. You mentioned at the end scope-safe metaprogramming or an application of this to that. Could you elaborate on that a little bit?
Yeah, so we follow the similar idea. So for example, we have the metaprogramming inside how to say that? We have a multi-stage programming. We need to allocate a next stage variable. And when we allocate the next stage variable, then we increase, then we also have this abstract type variable for it, and you can only use inside the lexical scope. So you can use, we guarantee that it will be bind, and we will not have open code that can be executed.
I see. Thanks.
Yeah. Next speaker, please come to start setting up.
Thank you. So somewhat related to question to, the previous question. So I'm interested in staged programming, and so I think effect information to code generation means that so it's safe to run program at runtime, like eval function, or it's okay to safely store code fragment to mutable state.
Sorry, I don't understand the
maybe we can discuss.
Yes, we can discuss later.
Okay, let's thank the speaker again. All right, next, Jayanaka will tell us about MTP. Please go ahead.
Okay, so my name is Jayanaka Dantanara, and I'm from University of Michigan and part of the Jessica research team. Yeah, so today I'm going to talk about our research project that we started like 2 years ago called MTP, a meaning type language abstraction for AI integrated programming. And this is the team that worked on this research and built the infrastructure for it. So let's start with the basics. So what is an AI integrated program? So when we want to use LLMs in our programs these days, there are two main ways that we do in development. One is to generate code that will be the program. And the other way is we basically have the LLM perform a functionality in your program. For an example would be a software like Cursor or Copilot in your VS Code, just like doing the thing, doing the inference in the back end. You are not interfacing directly with the LLM. You are going through their interface. So that is an AI integrated program. So it's basically a program that interacts with an AI model during runtime, not the code generation way. This is the when I say AI integration, it means it just interacts with the LLM during the runtime. Okay. So as a motivation example, I'm picking this game level generation example. It's a 2D game. Each level is going to be generated by an LLM. It's generating the map of it, and we just play the game. So this, for the map, this is the data structure that represents the map. So we start with the position. We have x, y, a coordinate of integers, and then we have the wall data type, which is start position, end position, both of position type. And then we have map, which is also which has walls. It's a list of walls, enemies, a list of positions, player, start position as a position type. And then we have level, which also contains other metadata along with the map object itself. Okay, so this is the representation of the same map we see on the right, and we are writing this function to generate the next level. And what we're trying to do now is, we could have done this traditionally. We can just hard code it, but today's day and age, many people would like to put an LLM in it. So an LLM is going to generate the next level for us, not the code, the level itself. Okay, so how do generally these next level, these functions are being programmed? The de facto state-of-the-art method is prompt engineering. Prompt engineering has been a pain for past 3-4 years. And to show you why it is a pain, so on the right is the code that you need to basically write, implement the functionality of the game level generation pipeline. So you start with a prompt to describe what the LLM should do, and then you need to specify the JSON schema that matches the type that you want to get as the output, and you have to specify that. And then comes the validation part. When it generates the output, you have to make sure that it adheres to the type definition, and then you have to convert it to the proper type and pass it as an output. So that's the entire workflow a prompt engineer should go through, which is additional complexity. Before actually start beginning the developing the code, getting into the actual coding part, you need to go through all of this to get the LLM in it. Okay, so what if I said we can automate everything? If we can automate everything, wouldn't that be nice? So that is what we try to strive for with meaning type programming model. Okay, so when we say meaning type programming model, this entire research stems from one key hypothesis. If a human can interpret your code semantics and identify the developer's intent, an LLM might as well. So LLMs are these days are pretty good at looking at some part of your code and understanding what you actually mean by that code without seeing the entire code itself. So for an example, here we have DOB of type string. You give the date there, and a human reading this would definitely know, okay, DOB, date of birth of string type, or else this function signature right here, French to English. Okay, you're translating from French to English. You have input of string type, output of string type. Okay, a human can understand. So can an LLM. So why do we need to write a prompt for this? We can just use this itself because this embeds the context for the LLM to use. You don't need another prompt to tell this thing again. So we build this MTP system to extract that semantics that's already embedded as context in your program to generate these prompts. Okay, we start with the actual abstraction itself. We introduce a language abstraction so that a developer can just say to our underlying system, okay, I have this function, use an LLM to do its functionality. Okay, so the abstraction that we introduce is the by keyword. So you have the level by LLM, and the LLM can be any LLM that you already have instantiated in your program, and you just say by LLM, and that signifies our underlying system, okay, this function, this context right here should be used to generate a prompt and do the inference with an LLM and provide the level typed output. And after implementing that, like just writing that as code, we have to extract the semantics or the meaning of that code to actually generate the prompt. We can't just put this code, source code itself, because this is not going to be the only code that's going to be in your program. There's going to be a bunch more. You don't want to put everything to the LLM. So we use a compiler pass to extract the semantic information, and we generate this MTIR, a meaning type intermediate representation. It's basically a subset of a symbol table that contains the information about your types and data structures in your program, which persists in runtime. So we have this empty runtime runtime engine, which basically combines this MTIR with the dynamic value bindings, and then generate the prompt, do the LLM inference, and convert the output to the specific type, and do error handling in the same system. So this is the entire workflow of MTP, or meaning type programming model. And let's take the motivation example that we looked at earlier and go through how it flows through our system. Okay, so we have the source code, the same source code. It can be in different files. You may have different modules that also handle other logic in your program. So you don't want to pass everything to an LLM. You need to extract the context that you really need. So you start with, okay, let's look at all of the context out there, because you can't just traverse files. You just need a symbol table like data structure. So we create a semantic registry specifically because we build this on a Python superset. I'll talk about it in a bit at the end. So you extract a semantic registry. It's basically a symbol table like data structure. We use that to, you can't like put all of that into a prompt. You need to extract, okay, we have this by call side here. Let's get only the semantic information that's relevant for that by call side. So we need to identify those semantics. To do that, we basically traverse the semantic registry and collect all the information relevant to the by call side. In this instance, it's a function call. You have the get next level, previous level, the level object. So you basically get, okay, the function name. I have the function name, nice. You have the input names, input argument names, and the types. Okay, now let's find how these data structures look like, and collect all that information and create this MTIR, which is a self-contained data structure that persists in the runtime. Now, this MTIR in the runtime, or the call time of that function, is combined with the dynamic variable binding. That's basically the values that lives in your program. You take those values and just build the prompt. So this prompt can be as simple as this, or it can be complicated. It doesn't matter. What we implemented is this simple. In our research, we found that simplicity works better with LLMs than giving complex, larger prompts. So we build this prompt, and you can see we have the values, and the MTIR information is embedded as plain text in the prompt. Like for instance, map object, you give an example about how this map might look like with the types and everything. Okay, yeah, so we generated the prompt, good. Now let's do the inference. So you have the prompt, you do the inference, and you do the output conversion. In this step, you already know what the output type is going to be, and depending on that output type, you can do the validation. If it fails, you can either do an error handling, or in our case, we did a correction loop. It's up to the implementation of this. You can either go with just error handling, or a loop that try to correct itself. But if it passes the validation of the type validation, then good. So it passes, and you just return the value that's generated by the LLM as the object. So when you call the function, it looks like calling a normal function. It's not different. I'll show you how the code looks like right now. So for the evaluation of this MTP, we basically picked two different baselines. So LMQL is one of them. They are actually a language, a model query language. That's what LMQL means, and which allows constrained output generation. And this is basically the code for the same get next level function, but you don't need to go through that. We analyze this in the paper. You can have more detailed insights in there. And this is DSPY, another 2024 ICLR paper. They use, they're basically focused more on like prompt optimization optimization framework, but the interface is much cleaner than using prompt engineering. So this is how MTP looks like, or our implementation. So we basically need to import the model, instantiate the model, use the by LLM annotation, and then call the function as a regular function. There's no difference there. Okay, so let's see how do we reduce the developer complexity in terms of AI integration. So we evaluated lines of code modifications or additions required for AI integration, and you can see MTP, the green bar, is low for all of these benchmarks, and it reduces the number of lines of code needed for AI integration by like 10.7 times, and definitely it's a less amount of work for integrating AI into program with MTP. We also do some user study that you can go into in the paper. In addition, we did accuracy evaluations with the LLMs, with different LLMs. There is some extended evaluation in the paper as well, but the key point that I would like to show with this slide is that with these different models, you can see there's a trend, like when you have bigger, better models, the capability of MTP shines. Like you can see from 4 turbo to 4.0, and even here you have 7B, 70B models, it's getting really well. So the key insight that I would say is that LLMs are becoming more capable at deciphering the semantic information embedded in the code itself. So MTP is performing better. So yeah. So to sum up, this is our contribution, our hypothesis, and our contribution is the by language abstraction, MTIR, and MT runtime. This is implemented in the Jaceki ecosystem, which is an open source Python superset, which is a type-safe superset of Python. You can check it out. And we built this by LLM plugin to that, which we add the by keyword and everything. You can just visit bylm.ai, or you can just join our Discord server. Yeah, thank you very much.
All right, thank you. Any questions?
Hi.
Yep.
Great talk. I was curious about prompt injection attacks. So it seems like you're sending a lot of metadata about the program itself to the LLM. Maybe, well, I mean, certainly the LLM provider now has this, but perhaps also the user could somehow, say, like, inject into the prompt something that will then expose the source code of your project to the user. I was curious if you had any thoughts about that.
So, sure. So let's think. That's a really good question. So, yeah, in this case, we are actually providing like semantic information about the code to the LLM. Yes, and in that case, to be honest, like what we're revealing to the LLM is just the type system in your program to give more context to the LLM. We are not like showing the exact code itself. We are not showing any control flow in there. What we are actually showing is just the semantics, the meaning of the code, like what this function name is. So I think in terms of like revealing a lot of sensitive information, we won't be revealing the exact code. We'll be just revealing the context. So I think I don't think that it can be a problem, but it is definitely something that we should look at and see like whether that's a real problem. Yeah.
Thank you.
Yeah. Thank you very much for that question.
Thank you.
Okay. One quick question.
Oh,
yeah.
Okay, I'll try and make it quick. Yeah, so just basically that near the start you said that this is based on the premise that an LLM is quite good at interpreting what code that has been written is supposed to do. We write a function, the LLM is good at understanding what it is that we tried to write, your translation example. But I don't know if I missed something in the framework that you presented here, it just looks at type information?
Yes. Right now it just, so this has been like, this paper was in work for like 2 years. This paper and in the state of the artifact that we submit for this paper is like year old. Right now we additionally provide in context like doc strings and other information as well, in addition to the type system. So yeah, we basically reveal how these types look like. So the developer does need to be aware of how to write their code in terms of how to define their data structures that is meaningful for meaningful in the code. Yes.
Okay. Thank you. Yep. So for the next talk, Yuyan will tell us about modeling reachability types with logical relations.
Okay. Hello everyone. My name is Yuyan. To present our work on modeling reachability types with logical relations. This is the joint work with Songlin, Guannan, Oliver, and Tiark. Guannan now is a sitter at the types. Okay. This doesn't work. Wait, what? Why this doesn't? Okay. So, as we all know that ownership system track resources, especially memory resources. After 20 decades research on ownership type systems, Rust finally make a successful adoption of ownership in system programming languages. So now the challenge is how to adopt ownership for languages that combine object-oriented feature and hierarchical functions for a language like Scala. Okay, sorry. So how are we going to, what are the venues to address these challenges? So the promising venue, I guess, now is that we switch the restrictive properties such as unique owners to descriptive properties such as tracking reachabilities. Therefore, our prior work proposed reachability types, track sharing, and separation in higher-order languages. Compared approach of Rust, we start from a liberal foundation, just tracking reachabilities and add constraints such as uniqueness on top of it. So we believe this is a suitable way to integrate ownership with higher-order languages. So now let's have a quick overview of reachability types. So our types track variables in type qualifiers. Here the type means the evaluation result from T can be reached by variable x, y, z. But other locations, but not other locations refer to other variables. One of the key ideas of reachability types is to allow user to specify separation. Here, the type tells us the two variable reach separate locations. Now, the type of the qualifiers on the argument here, the diamond, says the reachable location from arguments are separated from the reachable location from the function. Now we call the function with C1 is type error, call C2 is okay. So this is because we have the guarantee that our syntactic separation guarantee semantic separation. So based on our previous result, we proved the syntactic type soundness by using progress and preservation. Also, we proved the preservation of separation. Of course, we are not the only one who pursue these directions. In Scala's team, they designed capturing types, and they have the real-world implementation. Now, the open question, although we have some good result, and now the open question is, so what are the stronger method theory properties such as semantic soundness, termination, effect safety, and equational theory? So in this talk, we start from the standard logical relation for the simply typed lambda calculus with first-order references. We augmented with internal invariants to track the flow of store locations. without restricting expressiveness. Then we rediscover reachability types by propagating selected choices to user-facing qualifiers. So we use the, let's look at logical relations. This allows us to define some properties about types. So now let's look at the value interpretation of function types. So it tells us the closure value is valid at store typing sigma if we have some argument satisfied argument type at some future store typing. And then we evaluate the term will have some value, the value satisfy the result type. So this is the function type, and then because our program, the store always grows monotonically, so we use the store typing extension to model it. So this is consistent with the program semantics. And then we also, of course, we need to define some other like semantic interpretation of terms as well. And suppose we have all the definition, then we can prove the fundamental theorem, which says syntactic taxonomy is syntactic judgment implies semantic judgment. And then, of course, this gives us some very stronger result. And then, however, the kind of the property that we can entail is still limited. For example, let's look at this example. The program allocated two references, and then they have a function. The function updates one of them. Then we have the assertion want to say another value stored in the location are preserved. So with the logical relation we just saw, we cannot prove it. And also the assertion is an unsafe feature because statically we cannot not guarantee the assertion is always true. So this is, but however, this is an unsafe feature used in a safe way. So how can we, what's the problem is we lack of some local reasoning. So, but we all know some existing approach exists. For example, exception logic. So in exception logic is basically tell us we can have localized the store location to whatever the proof matters. So now instead of your store typing extension, we define relational store typing. It allows us to localize to the locations that are reachable from given values. Now we can use the relational store typing to define our function interpretation of functions. Now the sigma prime is will only related to sigma with the location reachable from the closures. And then the argument value is valid. Then we prove the program doesn't run. We got some values. So basically, this already gives us what's the Reynolds statement in the Reynolds paper. And then we can say a few more about some reachable information of the function argument result and the value preservation property, which is just a frame property. So, sorry. And then this is kind of a lot of formula. So now let's have a summary of what actually those formula tells. Those formulas just actually a bunch of semantic property. So basically, if we can have talk about some reachability information, we can say the argument overlap with either the closure or not the part of the closure. So if it's not part of the closure, we call it contextually fresh. Similar for result, it can be either overlap with the closure or the argument of fresh allocated location during the evaluation of the term. And then we can talk about observable effects, which are values stored not in the argument or the function. Those values will be preserved. It's something like a exception logic frame rule. And then now with this kind of semantic property, let's look at the identity function. Basically, we pass value A, we want to get some result that reach A. We pass value B, we want to get the result reach B. If we pass some fresh value, we want to get the result must be fresh. So this is just STLC. So the idea is, what if we expose this kind of semantic reachability information in the types? So this is exactly the motivation we have for the defined reachability types. So now let's look at the function type in reachability types. Our function type is qualifier dependent type. So basically, instead previously we just showed some summaries, some desired property we want to have. Now we are showing the qualifiers that actually can express this kind of information. So we can use some variable to say the argument overlap something in the environment, or use this symbol to say it's overlap with anything captured by the closure. Our diamond is the flash. Similar for the result. And then we can have observable effects, which are not touched by function and argument. And then we can just change our logical relation. Now we just interpreted of our function qualifiers. We got the desired reachable information in the logical, defined in the logical relations. Now let's look at this identity function again. Now we don't even have to look at the term, but just look at the type. We know that this is that's what it is. Basically, the type tells us you pass something in, then I will pass something out. So it gives us a precise reachable information. So then we can achieve some parametricity without explicit quantifiers. And then we prove the semantic sumness and the termination. And then we also define binary logical relation and to talk about the contextual equivalence. And we prove some two computation can be reordered if their observations are separate. So this simple program, basically, if two programs they work on separate memory locations, they can be swapped. Of course, this is kind of not desired because it doesn't have to be this way. We can do it more precise. Therefore, we add effect qualifiers to the function type. So the epsilon is just a latent effect. And then the same, the argument qualifier, result qualifier are the same. And then the effect qualifier have the same expressivity as argument qualifier and the result qualifiers. Then we can prove the reordering by using the effects. It's basically said read can be overlap, and then A cannot read A, please read. So basically, we see this problem, so we can prove their equivalence. So now let's say we can, by using the effects information, we can prove more reordering rules, enable more, create more optimization opportunities. So as a summary, today we present our semantic model of reachability types. We define the semantic type soundness, we got the termination, effect safety, and prove the program equivalence. All the results have been proved in Calc and can be found online. And also in our reachability types, we have some more recent result. So in the paper, we have the higher order store reference, but we can prove terminate, and which is kind of a surprise because we have some limitation in our type expressions. So in the Davis paper, we address this limitation to allow cycles. And then if you are asking about the annotation overhead, then we have bidirectional typing. In addition, we can leverage reachability qualifiers to do group reasoning like ARENA and to do memory management. And at the beginning of the talk, we said we want to build a liberal foundation and add constraint on top of it. So then today I only talk about the first part. Then the second part is actually can be found by Davis paper, the allocation and the ownership transfer. And then also we can, with the ownership transfer and something, and then we can have some, we can build the flow sensitive system to talk about type state. And then we can use that to prove the correctness of API use. And then today I just somehow implicitly say we have some encoding for capability and the effect system. But I don't have the formal connection. And then in the latest work, we have the formal connection. We also have a solution for affordable effect polymorphism without for our quantifications. So please take a look at our latest work. Can be found on the website.
All right, thank you. We may have time for one very short question. Anyone? All right. Otherwise, let's thank the speaker again.
Hopefully this works. Now, all right, cool.
All right. So for the next talk, 5 types Boolean algebras. Yes.
All right. Thanks, Lionel, for the introduction. So as he mentioned, I'll be talking about qualified types with Boolean algebras. This is joint work with my friends and collaborators at Aarhus, John and Magnus, and my advisor, Andre. So what's this talk about? So what's the motivation behind this talk? So you guys might be familiar with Flix, and if you're not, here's my obligatory plug for Flix. This talk brought to you by Flix. Flix is a relatively new programming language that is a multi-paradigm programming language with, for the purposes of this talk, what you should care about is a really cool type and effect system based on Boolean algebras with Booleanification for inference. Now that's great and all, but there are 2 major limitations with what we have in Flix so far, namely that there's no support for subaffecting, and there's not that much in the way of a formal foundation of what's proving the system sound. So the purpose of today's talk, or why we're going to talk about this, is we're going to try and fix that. We're going to extend Flix with a limited but sufficient form of subaffecting for the use cases we've seen in practical Flix programs. And we're going to present a rock formalization of a calculus system FB and FBE, which underpins the new effect system in Flix. So since this is OOPSLA, I should probably remind you what an effect system is. Effect systems augment type systems to track side effects of code. So if you write something down like print hello world, that produces a side effect. Formally, it produces an IO effect in string. You may want to record that to make sure to reason about what code can perform IO. Accept performs a network effect by receiving connection, and something even as simple as incrementing a ref cell performs an effect by mutating memory. So this is what our effect system in Flix looks like right now. Flix has a type system. It's statically typed, so that makes us all happy. And it will tell us that the minutes to when this talk should start, that's that function over there, is a function that returns int. That happens to be the minutes since the Unix epoch of when this talk should have started and when I should have finished this talk. Now, Flix's effect system tells us that minutes to talk may have the effect non-det because it calls a function, getCurrentMinute, that has effects non-det, and therefore itself could also be non-deterministic as well too. Purity in Flix, well, some functions are pure. If you're just comparing 2 numbers, well, you perform no side effects, and the annotation for that is just with the empty set. And of course, like any good programming language, Flix is also effect polymorphic. So here you can write down map. Map applies a function to a list of arguments, here restricted to int. And naturally, map has the same effects as the function it applies. So applying map to is overdue, which we saw earlier, is still pure. It has the effect set of empty. Now, Flix has a nice feature, which is pretty unique because it uses Boolean formulas for effect annotations, is that it supports a notion known as effect exclusion, where you can say, I can be effect polymorphic, but as long as you don't use some set of effects. So here, if you power map, which runs a function in parallel, it should accept most functions, but perhaps shouldn't accept functions that perform I/O, because those I/O effects might overlap in bad ways. So we might write that down in Flix as saying, well, f takes a function f that takes in an arbitrary effect set ef, as long as and f has to be parameterized by ef, but can't contain I/O. So you can now, of course, you can apply power map to functions that don't do I/O, like is overdue, and in that case, ef is filled in with something like I/O, where as overdue is empty, so IO minus O is empty. So there are some limitations to this story. So when one limitation becomes apparent when you try and perhaps write code incrementally in Flix. So if you wanted to write a program to send that monitors when this talk should be done, well, you might have to call a minutes talk to figure out when the talk should be done. You have to talk to a server that uses connect, which uses TCP connect as an effect, and you have to do some I/O, so that uses the I/O effect. So you use all these three functions. The effects fetch set of your program should be non-det, TCP connect, and I/O. So you start writing this function, and since you follow the principles on how to design program, you start by writing down its signature and incrementally building it up and debugging from that. So you might write down a small fragment that perhaps fetches the time to when this talk should be done, and then does some tracing, debugging I/O to help you build up your program. And you write down the proper signature, and you think, oh, this should work, but it doesn't because you get the problem that, well, the Flix compiler will tell you that it can't unify the effect formulas non-det, TCP connect, and I/O against non-det and I/O. Now, what's the problem here? Well, the problem is that we said that report time would do 3 effects, but the fragment we've implemented so far only does 2 of them, non-det and I/O. It doesn't talk to a server. And what we need to fix this is some notion of sub-effecting, because, well, some programs and expressions are unfairly rejected, just like this. And this has real consequences in Flix as well, too. There are 47 unchecked effect upcasts in Flix's standard library, and they're there because of reasons like this. And we'd also like formal foundations. So the idea we're going to do to fix both of these is we're going to build up on some work that does type qualifiers with lattices and polymorphism. Now, so that brings us to what we've done so far. So we want a calculus with a type and effect system that has parametric polymorphism, language effects that is described with Boolean algebras and Boolean formulas, and a sub-effecting relation based on set inclusion accounting for effect variables. So there's a lot of work on effect systems out there, but there's few grounded on anything like Boolean algebras. Coincidentally, like the closest system that we're thinking of was a system that I presented last year at OOPSLA, which combines some pretty cool work from 1999 of Jeff Foster on type qualifiers, but unifies that with polymorphism and sub-qualification through qualifier variables with the sub-effecting based on, and we use that to implement an effect system with the sub-effecting based on the lattice order. Now what's missing is that lattices are not Boolean algebras, but Boolean algebras are thankfully lattices. Every Boolean algebra is a lattice. Top and bottom in the Boolean algebra is the same thing as top and bottom in the lattice, and what's new, the only difference between a Boolean algebra and a lattice is that you have 2 new rules for dealing with Boolean algebras, namely rules for dealing with negation, and you have to be able to distribute meets over joins and joins over meets. So we formalized that, and it's actually not too hard. If you add those 2 or 3 extra rules to account for the extra Boolean algebra properties, you can turn a system on lattices into a system on Boolean algebras, a qualifier system on lattices to a qualifier system on Boolean algebras. And we can use that to build an effect system, the rules of which are right there. But I don't want to bore you with that, so if you're interested in how that's done or in the rock proofs, I'll kindly refer you to the paper. Now, that's really nice in theory, but we also want some results in practice too. The system I've just shown you gives you a formal model for a potential Flix system based on Boolean algebras in Flix, but how do we actually implement this? Because Flix comes with an already very powerful system for type and effect inference based on Boolean unification. Adding general subtyping and sub-effecting can be a bit messy. And if we actually try and do that, it would be a bit messy, and we leave that for future work. But as it turns out, for the applications we've run into in Flix, we can get away with 3 limited forms of sub-effecting. Sub-effecting at an abstraction site where you allow variance, you allow the effect set of a lambda to vary to be a little smaller than the effect set of the context that expects it. sub-affecting a definition site, where you allow the effect of the body to be a little smaller than the effect of the declaration, and I guess similar to that, sub-affecting an instantiation site, where you allow the effect set of a trait definition to be a little smaller than the effect set declared at the start at the definition of that trait. And if you implement all three of these things, you can actually get rid of most of all the cases where we see upcasting and flicks. Now, how do we do that? Well, concretely, we have this Boolean unification engine that allows us to unify effect constraints involving equalities. If we want sub-affecting at these three sites, then all we need to do is add a slack effect to the unification constraint to allow for sub-affecting or slack. So concretely, in our example that I filled earlier, you would unify the body against effect variable B, you would unify, but you would allow for some slack between unifying that effect variable B against the declared effect set of that function. So here, you could, when you do the Boolean unifications, you could sub in B as equal to, well, the calculated effect set of the body, which is non-det and IO, the slack to be TCP connect, and it all just type checks well. So empirically, this gets rid of all the upcasts in the standard library, and the performance impact on type and effect inference when you actually compile code in Flix is under 5%, which is really nice. Even though you introduce all these slack variables, you don't really mess with the compiler and its performance. So you can still compile code practically. So what have we done? We've presented a qualifier system that we've used to build up an effect system based on Boolean algebras in Flix. This can also be used to go and implement other systems that we've also seen in Flix, such as on restrictable variance, nullability, and information flow. And we've implemented this nicely in Flix, and we've shown that you can use this to remove all the effect upcasts in Flix's standard library, making it more usable and more safe. So if you're interested in the proofs, like the artifact and the papers are all online. And if you're interested in playing around with Flix and our new sub-affecting system, you can download it at flix.dev, and right now you'll have to turn on the feature flag, but shortly this will be live in the mainline Flix distribution. So thank you.
All right. Any questions? Okay, so I have one question. How does this compare with the system we presented earlier?
That's a good question. So I think both systems are cool, but I think they approach the design space from two different approaches, right? So with the system that was earlier presented, right, you have a more general system involving negation on types, which allows you to which I think allows you to do some really cool hacks to the type system, but it also comes with some complexities as well too, right? Whereas here, we're just looking at just a simple adding negation in specific and certain restricted locations, namely in qualifier position, right? So you don't get as much expressivity, but you also get a simpler system. So I think there's space for both in the design space. It's just a matter of how expressive you need to be versus if there's a need for simplicity in your type system as well too.
All right, thanks. Fair enough.
Thank you.
We have more questions. So.
Oh, wow, all right.
Hi, I'm Christo from Insight. I was wondering about the effect system of Flix. If a new effect is added in the future, let's say does blocking I/O or something like that.
Sure.
And it needs to be added to the standard library, would this break all client code, or does the language have a way to say this function has whatever effect so that any standard library changes don't affect it?
So I guess when you add a new effect, you're asking if the standard library changes wouldn't break it?
If user code would need to be adjusted to mention that effect as well?
No, so I don't believe it would break right now. But I guess if we want to talk about this more offline, I'd love to.
Okay.
Okay.
Thanks. Yeah, sometimes in Flix we have things like an iterator, which is parametric over some effect.
Right.
Does this just work with that kind of thing?
So it works. So I believe this should just all work with Flix with the iterator trait with Flix. In fact, it gets rid of one really annoying problem with the iterators and mapping, and that, like Flix's iterators are all done in a weird continuation passing style, and that needs upcasting because of, well, the base case of the continuation has no effect, and whereas mapping could have some effect. So this actually fixes the problem with the iterator system.
Okay. Thank you. All right, so next, Jeffrey will tell us about path-sensitive type inference.
All right, thank you. So this is a paper on path-sensitive type inference for REST APIs. This is joint work with my student Mark Aldrich, who couldn't be here today, Kyla Levin, who's now a PhD student at UMass, Michael Koblenz, who's here. And so let me start by reminding you a little bit about REST APIs. So I'm sure you've seen these and quite possibly used them. They're super common, right? So what REST APIs are web services. So instead of connecting to a web page and browsing it, these are things you programmatically connect to. So here's an example on the upper right. We send a GET request. So there are a bunch of different actions you can take, different verbs, to the products endpoint. So that's a particular web service, and we get back an HTTP response that's usually JSON. That's taken over the world, so that's what everyone uses. So the response has the JSON code. So here we can see we've got carrots and potatoes, great. And there's also a success status. The 200 code indicates that was a successful request, great. We can do a post to say we have some lettuce. So that's a different connection to the same endpoint, and we get a different status code back. And then if we do a lookup, fine, we can see we now have carrots, potatoes, and lettuce. So these things are great. They're super popular. They're used all over the place. They look very intuitive. You can read them, and you can use your intuitions to understand how to use them. But like any piece of software, they get complicated and tricky in some cases. So for example, in the upper right, maybe we are trying to get the list of products, but maybe we actually have to be logged in before we can do that. So actually, we don't always get success. Sometimes we get an unauthorized response code. Or the next one, maybe we do a post request, and we think we can just add lettuce without a quantity, but instead we can't do that, so we get an error code, which maybe we weren't expecting. And then maybe we're logged in the lower right corner, and we get the list of products, but we don't have full permission, so we only find out which things we have and not the quantity of each one. So what seems like a really simple interface can actually get complicated quickly. And so there's really a need for specifications for these APIs. And that's not just me saying this. There's a rigorous language called OpenAPI for writing specs for these things. And it's extremely common. And if you look up all the major APIs that major providers have, they have very detailed specifications in these languages. So how do we figure out what these specs are? I mean, we could just assume that people will write them down, and you know how well that works. And it works pretty well for major players, but there are lots and lots and lots of these APIs all around. So in the upper right corner, we've got some code. This is in Ruby on Rails. So everything I'm going to tell you about the type system is built for Ruby and Ruby on Rails, which is a web framework for writing web servers. So this is the code that gets called when a particular endpoint is invoked. So I didn't give you the name of the endpoint, but you can see the method is called createUser. And it's got a little logic here. It says if there's some global setting, invite only, that's false, then we just go ahead and create a user. We return the success status code 200 and some JSON with the words OK in it. And otherwise, we indicate a failure that this is unauthorized. So right now, to infer this kind of specification, the state of the art, the thing that people actually use, is dynamic inference. So they take a test suite, and they run it against the web server, and they stick a proxy in between to sniff the traffic, and they take everything they see, and they turn that into a specification. Now, of course, you could run this on the actual website traffic, but people don't usually do that because there could be sensitive information and you'd be slowing down your web service. So usually you use test cases. And whether you use test cases or the actual traffic, you're going to miss things, right? Dynamic analysis only sees what's there, not necessarily what's possible. So we might see the post users, we might see the success case, but maybe no one did the failure case because that option is disabled, and so we just don't see it, so the spec doesn't have that information. So the next idea, since this is a session on type systems, is to use a type system. And so we could use type inference. So if we run standard type inference on this, we can get some useful information back that covers all the cases, but is kind of imprecise. So here we look at that code, and we can see, well, at the end of that, status is going to be either 200 or 403. And those are singleton types, so we just lift the integers into types representing themselves. And then the JSON, we can see that, well, we might get either success or failure, and those are optional. That's what the question mark indicates. And this is helpful, but it doesn't quite give us what we need to use the API because it's too imprecise. So the idea that we introduce is to do a path-sensitive type system. And so the way we're going to do this is we're going to sort of borrow ideas from symbolic execution, where as you simulate the program, you accumulate a path condition, keeping track of which branches you took under conditionals. So a path type here is going to be, well, here it's a pair, but it could be an arbitrarily sized tuple, where there are these path conditions phi1, or in this case phi2, that tag types T1 and T2. And the way to read this is if each phi I holds, then this type represents type Ti. And the way these are set up in our type system, the disjunction of the phi i's always evaluates to true, so there will always be one arm of this under any path condition that you can pick. So this is going to let us keep track of very detailed information about what happens in one of these endpoints in this Ruby on Rails code and produce very precise, useful API specifications. So here's an example. So we've got the code on the upper right. The left has the type system as it follows the control flow graph at just a few key points. So initially, the JSON is just empty. I sort of hard-coded that in there to make that obvious. The path condition is true because there's been no branching. And if we go left, so if we take the true branch, then the JSON contains success, which is a string, and site setting invite only is false. If we go right, we get failed, and site setting invite only is true. And then when we merge, we get one of these path types that keeps track of, well, you can see it. It says if site setting invite only is true, then JSON will be failed. If it's false, it will be success. And then you can see the same thing for status. So we've got two super useful things here. One is that we can tell under which condition we get the different types for each possible variable in our program for JSON and status. And we can see correlations between them. So path-sensitive types or path-sensitive anything, one of the major uses is to look at correlations. So we can see that, you can see in the lower right corner, that if site settings is invite only is false, we get 200 and success. Otherwise, we get 403 and failed, which is exactly the information that we want. So that's what we did. I'm going to show you some results in just about a minute. Let me point out one problem with this. So it works remarkably well for a lot of code, but these web servers have a lot of business logic in them, and sometimes business logic is weird and quirky and big. So on the right, you can't really see it in detail unless you have super good vision. There's a huge stack of conditional ifs, and this comes from Canvas. And if you look at the control flow graph, it forms this kind of diamond pattern. And if you think about the number of paths through this sequence of diamonds, it's exponential, right? Because you could go left, right, left, et cetera, right? So if we use the approach I just described, this blows up. It doesn't work. It doesn't scale. And fortunately, there's a fairly simple trick we can play to make it scale to those examples. So what we can observe is that we can sort of push the implications down under the types or under the hashes and then we can represent things in a more compact way. So, if you look at the top in this example, so initially hash is empty, then we update, if x is true, we update key 1, if y is true, we update key 2, and then in either case, we update key 3. So, if we go left from the initial state, we can see the hash has key 1 in it, which is A, otherwise the hash is empty, so we merge those together, and we would get x is key 1, not x is empty, and then we would split, and we would get these 4 possible cases down here at the bottom. We have exponential blowup. Instead, what we can do is this. So we can split, and then when we merge key 1, we can push the implication down under key 1, and we can say key 1 is either, if x is true, it's A, if x is false, it's bottom. So that seems very simple and like it's not going to get us much, except what we can see without doing any complicated analysis is that when we then write to key 2, we don't have to look at key 1 at all, because key 1 and key 2 are completely different keys. They don't have to do with each other, and we don't have to do any sort of scanning over the type to figure that out. It's sort of instantly available, which means we can play the same trick again. We can get the 2 branches. One of them has key 1 as B, the other doesn't, sorry, key 2 as B, the other doesn't have key 2. And when we merge them together, we then get this type down here where we have 2 different types for key 1 and key 2 that represent all 4 possibilities, but in this very compact way. And so if we keep going, we'll finally get a simple type on the right where key 1, key 2, and key 3, when we go to add key 3, we can just add it in. We can ignore key 1 and key 2. We don't have to do the exponential blowup. We don't hit that case. All right, so let me quickly show you the benchmark results. So we ran on a bunch of Ruby on Rails programs that have REST APIs. These are all very large programs, so we weren't able to analyze all the code, but we could analyze a total of 132 endpoints in them, roughly 4,000 lines of code. We found, when we compared to dynamic analysis, so I'm comparing 76 endpoints because dynamic analysis didn't hit all the code. There were lots of cases that the test cases never even saw. We can compare the dynamic specification inference to the REST Pi inference with this static type system. And you can see that for the HTTP 200 cases, those are the success cases. We got a couple more of them using REST Pi. But where we really got a lot more is in the other cases, the error cases, the cases where something weird happened. We were able to infer many more specifications, 165 instead of 72. We didn't miss any fields in our static analysis. We found them all. We found a lot of additional fields that never showed up in testing, a total of 985 fields that were never mentioned, that you never saw in the dynamic tests. The dynamic tests were driven by test suites that came with the programs. And we also found a lot of cases where the test suites appeared to require a field because it always showed up in the output, but it turned out the field was actually optional if you looked at the code. And then the path merging thing that I went over very quickly, it turns out to be really important. So in the upper right corner of the right figure, you can see we got a bunch of timeouts in several of our examples because of exponential blowup. And those timeouts turned into, we could just run the code and get the result sort of quickly. All right, so REST Pi performs path-sensitive type inference with path types. Merging is important. It lets us scale to large, complicated control flow, and it finds more and more accurate specifications than dynamic analysis. You can look at the paper to find out about handling layering of endpoints. And future work is actually interpreting the path conditions. Right now, we leave them uninterpreted, which turns out to be OK most of the time. We can just look at them and understand. But there could be interesting work in actually interpreting them for deeper analysis. All right, thank you.
OK, thank you. We have time for a quick question.
So maybe I said this. So if the path condition is a function call, so right now you just keep the function call as is.
Say that again.
In the path condition, rather than saying x greater than 0, I'm going to say f of x plus y of z.
Yeah. So whatever textually syntactically shows up, that's what we treat uninterpreted as the path condition, that's what we accumulate. And a lot of the time in the code, it's actually very understandable because the way this code happens to be written.
Also, what's your ground truth? When you find the type, how do you know it's correct?
So we did manually compare to the dynamic analysis, and I mean, it looks correct from everything that we can tell. Yeah.
Thank you.
All right, thank you. Let's thank the speaker again. Okay, so for the next talk, Russ will tell us about type outference. All right.
Hi, I'm Russ Tate, and I'm excited to be presenting this work I've been doing with the Kotlin team in order to make their type system decidable. The team views decidability as not just an academic principle, but as something that can provide real pragmatic value for them. In particular, they see it as a means for providing a reliable and stable programming language that has a declaratively specified standard that's easy to extend with oft-requested features. And the work I'm going to present today seems to lay the foundations for making this possible. Now, you might think that decidability is difficult because Kotlin is a large language. But in fact, decidability for even just core object-oriented features has been an open problem for decades. For example, consider this simple program. Now, it is the case that algorithms by both Kotlin and from the literature can validate this program. However, if I make this change, then that's no longer the case. And to see what goes wrong, we can look at what happens with Kotlin. So with Kotlin, this loop variable, it infers its type to be foo any because that's the principal type of its initializing expression. However, that causes this later assignment to get rejected because the foo of any returned by bar is not a subtype of foo any because foo is contravariant rather than covariant. As for algorithms in the literature, this program is simply out of their scope because this interface is irregularly recursive. That means that the types in the program cannot be represented structurally using just a finite graph, which these algorithms rely on in order to ensure termination. Now, you might be looking at this interface and thinking, this doesn't look very realistic. Maybe this isn't a problem in practice. But let's take a look at some examples of method signatures taken from standard libraries across industry languages. Here are examples from Kotlin, Java, C#, and Scala. All these examples are generic, and many are furthermore irregularly recursive. And this is problematic because both these features by themselves are known to make subtyping undecidable with structural types. And while in this paper, I only show how to address irregular recursion, the point is that we can't rely on structural techniques alone to solve this problem. We need a fundamental new insight in order to scale to the expressiveness used in industry. So going back to our program, notice that our interface has a name. In Kotlin, this name is significant. That is, even if two differently named interfaces have the exact same structure, Kotlin will still view their types to be distinct. That means that Kotlin generics are nominal. And one of the key contributions of the paper is to provide an algorithmic technique for taking advantage of nominality. To illustrate it, I'm going to walk through how we validate this program where others cannot. And for that, I'm going to rearrange and space out the program to make a simpler, easier visual. So the first challenge is the fact that this loop variable has no type annotation. And we're going to address that challenge the same way many others do. We're going to introduce a type variable L to represent its type. And here I put a little circle over it to indicate that it's a hole in the program that we have to deal with. The second challenge is this bar invocation. We have to resolve this bar. And what Kotlin does is it resolves it based on the preliminary best guess of the receiver's type, which in this case is foo any, and that's overly precise, causing the problem to get incorrectly rejected. Whereas what algorithms from the literature do is they turn this into a structural constraint, and that turns out to be too relaxed, causing them to fail to terminate on this program. So what we do is we introduce an event-driven technique. We install what we call a label listener. This listens to the type of the receiver L. More precisely, it's going to listen to changes in information about the label of that type, such as the name of the interface that it belongs to. And as it learns information, it's going to dynamically generate constraints that reflect how that information affects the validation of this indication, which I'll illustrate later. With that label listener installed, we then move on to standard constraint collection. So for example, here we have foo any. That's the type of init that flows into loop. And as such, we know that foo any needs to be a subtype of L. Now we could go on, but for the sake of illustration, I'm going to jump into illustrating what effect this constraint has on our algorithm. In particular, from this constraint, we know that the label of L is at most foo. That's new information that we just learned, and as a consequence, our label listener triggers and reacts to that, in particular because now we have enough information to resolve the bar method. Knowing just about that label, we now know that this bar method has to be resolved using this signature from the foo interface. And so the label listener will then generate constraints to validate against that specific signature. Now, the first thing it has to do is say, okay, well, the receiver needs to be valid, so loop needs to be a foo, but we don't necessarily know what it has to be foo of. But label listeners are allowed to introduce more type variables, and so it'll just introduce an A and say that L needs to be a subtype of foo of A for some A. It can then reuse that for validating the rest of the method. So in particular, this argument is valid if L is a subtype, or A is a subtype of L, other way around. And the result is assignable to our loop variable if foo of A is a subtype of L. And at this point, there are no more direct flows we have to capture as constraints, and we've extracted what we call the graphical core of the program. Now, in reality, the graphical core of the program contains that label listener, and I've just sort of partially processed it for the sake of providing a simpler visual. In general, graphical cores can contain unactivated label listeners that are allowed to dynamically generate more type variables, constraints, and even more label listeners, so long as they do so in a well-founded manner. Thus, graphical cores provide a means for extending traditional techniques with label listeners as a way to dynamically react to nominal information. But at this point, we've extracted sort of the essence of the validity of this program, and so we can throw the program away and just reason about this graphical core. Traditionally, we would do so in the context of type inferability, where the key question would be, is there some solution for L and A that satisfies these constraints? And I'm going to jump ahead a bit and say, well, there are existing algorithms already that can solve these constraints and to give you that this is a solution for L and A. Now, these are complicated types, but there also are existing solutions for often being able to reduce types to sort of more compact recursive types. But this is still problematic for us because Kotlin doesn't have recursive types. Now, we could, of course, always extend Kotlin with recursive types, but we found that even if we do this just behind the scenes, it still causes problems for users, for the compiler, and especially for our proofs. Nonetheless, this program is safe, so we would like to be able to accept it. This prompted us to look into whether there's some other notion of program validity besides type inference that wouldn't require these convoluted types in order to accept this program. For that, we explored a new perspective. We said, rather than viewing L and A as unsolved types, what if we thought of them as abstract types? And these collected constraints are simply the assumed subtyping properties for these abstract types. Well then, I've just defined a custom type system where my program type checks. So which seems great. But on the other hand, I've just defined a new type system. So how do I know this type system is safe to use? And that's where the rest of the algorithm comes in. Rather than exploring, is there a solution for L and A, it's exploring, is this a safe type system to use for my program? And already the constraints sort of capture the direct flows in the program, and we can see there's nothing like obviously wrong, like an integer flowing into string. But they also enable a bunch of indirect flows, or imply a bunch of indirect flows, and we have to consider those as well. So we're going to analyze these constraints in much the same way that other existing algorithms do, but with a different perspective on what these steps is going to mean. For example, here I have foo of any flowing into L, and I have L flowing into foo of A. So I have this indirect flow, and I need to know that foo of any is a subtype of foo of A to know this indirect flow is necessarily safe. However, that's not true with the constraints I've collected. But this program will still type check even if I add more constraints to this system. So I could add that A is a subtype of any, which at least locally seems perfectly safe to have. And now we have the required subtyping. And I can do this for more direct, indirect flows in the program. Here, learning that A needs to be a subtype of foo of A. And here, learning that foo of A needs to be a subtype of A. And then here, I learned that foo of A needs to be a subtype of A. Oh, but in that last case, I already know that. That's already present in my constraint system. And I've reached a state wherein all the subtypings required for these indirect flows are in fact implied by the constraints I've derived. As such, we call this graphical core consistent. And if we reflect on this process, notice that in every step where I derived a constraint, I always derived constraints between types that were already present in our collected constraints. That puts a finite cap on this set of constraints I can derive, which ensures this process terminates. Even if I add label listeners that can dynamically generate more types and constraints, they are sensitive to only label information and as such can only fire a finite number of times, still ensuring termination for this process. This means that graphical core consistency is decidable. Furthermore, because I've reached a state where all the required subtypings are implied by the constraints, I was able to show that this means this type system, custom type system, is safe to use. This prompted us to define this concept of type consistency, wherein a program is valid if it can type check within some consistent type space. Type inferability then is just a way to establish type consistency where you're using a predetermined consistent type space. On the other hand, type consistency does not ensure type inferability, so we can't call our algorithm the type inference algorithm. So as a pun on the fact that our algorithm works by sort of factoring these type variables out of the constraints, we call decision procedures for type consistency type outference algorithms, and introducing sort of a generalization of type inference. Now, I recognize that this is kind of weird and far-fetched, so I formalized and mechanized all of this in Rock to establish confidence in these results. I proved that type consistency does indeed ensure progress and preservation, even if we don't get a solution for the constraints. I proved that user-expressible types form a consistent type space, which means that any program that is inferable using user types is valid according to type consistency. I proved that graphical core consistency is decidable even with these label listeners able to dynamically generate more types or variables, constraints, and even label listeners. And I proved that I combined that with that process for extracting a graphical core from a program to prove that type consistency for programs is decidable. All this can be found in our reusable and reproduced artifact that's available online through the ACM Digital Library. So now, hopefully that explains the title of this paper. This is a foundations paper because it focuses on just core object-oriented features. It achieves decidability by using event-driven label listeners as a way to dynamically react to the nominal information present in many object-oriented languages. And it introduces type consistency as a more relaxed but still safe notion of program validity, sort of replacing or extending the concept of inference to outference. As I mentioned in the beginning, this is sort of a first step in our work. So if you're interested in how we've extended these concepts to the much larger Kotlin language and extensions we're building thereupon, feel free to come, or please come find me afterwards. Thanks very much, everyone, for your attention, and I don't know if there's any time for questions.
All right, thank you. Questions? Yes.
Hi, Ross. I was curious, you're doing this in the setting of Kotlin, which in addition to having all the things you showed, also has overloading. Does that wind up complicating the story at all?
Yeah, so overloading is, in some ways, it complicates it in that, yes, overloading just makes things necessarily messy in provably hard ways. The other way, it makes things messy in a way that we can't really improve upon, so you can kind of plug and play like a overloading semantics, and it has the obvious interplay with these kinds of features. This what I've presented so far is polynomial time, whereas overloading provably makes it not polynomial time. But our goal is that essentially if you have a system where overloading is well designed, they've made libraries that have these nice behaviors, it'll always still perform polynomial time and have good semantic guarantees. Oh, yeah, sorry.
We still have time for one quick question, if you want. There was another question. Okay. Okay, so next, Adam will tell us about flat closure optimizations.
Thank you. Can everyone hear me okay? Awesome, let's go. So this is the type session. I think we can all agree types are cool. We like types. They allow us to reason about safety properties of our programs. Awesome. I happen to like compiler optimizations also. I think those are also cool. They make our programs harder, better, faster, stronger. I'd really like to have both of these things together. I would like to have type-safe compiler optimizations. Unfortunately, we don't have that always. And as you may have guessed, what I will be talking about today is that in closure conversion, we don't have both of these. The state of the art for typing closure conversion does not permit common closure optimizations. And that makes me sad. But what if I didn't have to be sad? What if we could type these optimizations? And yeah, that will be this talk. So let's go. What is closure conversion? Well, we have this program, and in this inner scope, we have this local function, and it refers to these local variables x, y, and z. But when we want to lift this to the global scope, we can no longer refer to x, y, and z because they're not in the global scope, they're in this local scope. This doesn't work. Instead, we need to find a way to bring these variables back into scope, and how we're going to do that is we're going to introduce an environment parameter which will contain the values of these variables that we will project out. Then we're going to package the value of these variables into an environment which gets packaged together with this function, which will get passed to some end user. So Santa's elves have given us this package. Santa's brought it down the chimney. It's Christmas morning. We want to unwrap it and play with it. What we need is a closure calling convention. So what we want to do, the first thing, is project out the code pointer somehow. Second thing we want to do is project out the environment, and then we're going to want to pass the environment to the code pointer. But what we don't want to do is pass in some value that does not have the right shape, does not have the values of all of the variables to the projected code pointer. And this is really the key safety property of closures that we want to verify, that the projected code pointer is called with the packaged environment. Now let's talk about the optimization. The flat closure representation was first introduced about 40 years ago by Cardelli. And the idea is that the closure is represented as this flat structure containing the code pointer and the values of the free variables. And one of the nice things is that the closure is the environment is the closure. So why is that nice? Well, that means that we can simply project out the code pointer and then pass the closure itself as the environment to that projected code pointer. And that means that we only have to do this one projection instead of these two projections. And if this is a recursively called function, that can really add up. So this is the main optimization I want to type, the flat closure representation. We want both of these things. As we're about to find out, the state of the art doesn't support both of them. What is the state of the art? It's the existential closure representation. We're going to give the closure an existentially quantified pair, where the type of the environment is what is being existentially quantified over. So we project out the environment, and it has the existential variable type. And we project out the code pointer, and it's expecting that existentially quantified variable as the type of the environment. But because this is a pair, we see that we're doing these two projections, so this doesn't support the flat closure representation. We have our speed, but we don't have speed, but we do have safety. Now, our approach is the flat closure calculus, or FCC. And we use the flat closure representation, so we have speed, we have the optimization, rather. Fantastic. But how are we going to type check this? So when we form a closure, it has the closure type, but as you may notice, this closure type has no reference to the environment type. So how do we know that when we project out the code pointer, we're going to call it with the correct environment type? In other words, what type do we give to the projected code pointer? Now, again, in the flat closure calling convention, what we want to pass as the environment is the closure itself. So what if we just put the closure into the type? And we can do that using a singleton type. And really, this is the key insight of this paper, that the singleton type perfectly captures the safety property of the flat closure calling convention. Now, of course, because we're using a singleton type, this introduces some dependency into the type system, so we have to add some restrictions to make that work, and we have to add a few lemmas to our type safety proof, namely substitution and some well-formedness. We also have to make sure that the closures are formed properly, but that's an easier problem to solve. So in FCC, we have both the optimization, we support that, and we also have our safety property. But of course, because we don't have a lot of time for these talks, I have been lying, and I will tell you the truth because it makes us look even better. I said we wanted these two properties for safety and the optimization, but there's actually a whole bunch of optimizations for closures who've been pretty well studied. And so we actually come up with 7 requirements for FCC in the paper, and we show that we support all of them, and we can do a bunch of really cool stuff with closure optimizations compared to prior work. So of course, in the paper is all of the meta theory. There is an implementation in Redux of the type system, the language, and optimizations. We also have more optimizations described in the paper, which can be done in a type-directed way, and we give a type-directed formalization of some past optimizations. We also provide a type-preserving translation from the abstract closure calculus. So this is basically a way of showing how you could fit FCC into your existing compiler, even if it's a type-preserving compiler, which is pretty cool. Yeah, if you're interested in more stuff on types and compilers, my co-authors gave a bunch of talks earlier this week, so you can go check those out. And I think I'm going to give you back some extra time to go enjoy break. So thank you.
I'm going to start with a short, maybe cryptic version of this question, and I can expand it as needed. I'm curious if you also considered using row types to get to the same result, and how does that fit into your big table of check marks that you showed us?
Yes, that is a fantastic question. We did, in fact, consider row types, and one of the kind of hidden motivations for this work is that some of my colleagues are interested in doing dependent type preserving compilation, and they have a problem with the existential type because it quantifies over types, which causes issues with impredicativity with dependent types. And we found that the same problem was present when we were trying to do row polymorphism. So that's why we wound up using the singleton type. But we do speculate that for the purpose of the optimizations, it could probably work. Thanks. But we haven't studied it in detail.
Hi, nice work. So I wanted to ask about your closure to result type. I mean, you didn't actually show in the talk what the type would be. And the related thought here is, can't you just use recursive types for that? Because you're passing the closure type. It was closure arrow B.
Let's see. So here, is it?
Yeah, so that type over there.
Yes.
Should we be reading that as closure from A to B to B?
What I mean is that like the box that you extract the code pointer from is what you pass in as the environment. So that's a singleton where the only inhabitant is whatever closure you projected the code pointer out of.
And so then, instead of using singleton types, do you think it might make sense to use recursive types?
We do use recursive types.
But that wouldn't give you the guarantee you get with singletons.
Yes, so we do use recursive types for the representation because there's an inherently recursive relationship between the type of the function and the type of the closure because the function is part of the closure and it also expects the closure as an argument. So we do use a recursive type for that, for the representation, but then we have this kind of more abstract notion that uses the singleton type to enforce the calling convention.
Okay, all right, thanks.
All right, we have time for more questions. I guess if there's no question, then we can go to the break. Let's thank the speaker again.
Okay. So welcome everyone to the languages session. So without further ado, let's move on to our first speaker, which is Kartik, and he's going to tell us about probabilistic programming.
Y'all hear me? Yeah, great. Thank you all for being here. I'm Kartik, and I'm going to tell you about Memo, a new programming language that I've been working on. I wanted to start this talk by playing a game invented by a philosopher named David Lewis. And here's how the game works. You're sitting at a table, and at this table are 3 objects, a pink circle, a green circle, and a green square. And sitting across from you at this table is your partner or your teammate. It's a collaborative game. You're in it together to win it together. And your partner is randomly assigned one of these 3 objects to communicate to you. But your partner is only allowed to use one of 4 words to communicate. Your partner could either say round, green, square, or pink. Okay, so suppose your partner says, can you please bring me the square one? Can you all just point for me which object would he pick? Come on, guys. Great, strong preference for the green square. It's the only square one. Suppose your partner says, can you please bring me the pink one? Can you guys please point for me? Which one would you pick? Great, strong preference for the pink circle because it's the only pink one. But now suppose your partner says, can you please bring me the green one? This one's harder because there's 2 green objects, the green circle and the green square, so what are you supposed to do? Well, perhaps surprisingly, people tend to have a preference here, and the preference is for the green circle over the green square. This is a real phenomenon, it's robust. Here's some data from a replication by Ching and Franca in 2015 where they found that about twice as many people pick the green circle over the green square. So what's going on here? What's breaking the symmetry between the 2 green objects? Let's try to analyze this game as we would analyze any game. Suppose I am the listener in this game, and suppose I heard the word green. Well, we just established that a priori it's just ambiguous whether it's the green square or the green circle. But when we play games, we don't just play at the literal level of the rules of the game. We think strategically. We think recursively about how other players in the game might be thinking. So let's think about how my partner, the speaker in this game, might be thinking. Suppose she's trying to communicate the green circle. Well, she could say green, which is ambiguous, or she could say round, which is also ambiguous. So my partner is actually also in a bit of a pickle. But again, suppose my partner is not just thinking literally, she's thinking strategically, recursively about other people in the game. Then an interesting thing happens, because my partner can do the following thing. She can say, Kartik knows that if I were trying to communicate the green square, I wouldn't say green, I would say square, because square is unambiguous. When I said square, you all pointed to the green square. So Kartik should be able to infer or deduce that if I said green, the risky, ambiguous utterance, then I was probably not referring to the green square. I was probably referring to the green circle. Does this reasoning go through for everyone in the room? Can you guys nod for me? Yeah, okay, fantastic. This way of thinking about how words tend to get meanings in everyday pragmatic language use is called the Rational Speech Acts framework. And it's been very, very successful, very influential in cognitive linguistics, in part because if you were to write down a computational model of how you would do this recursive probabilistic reasoning about people thinking about each other under uncertainty, you would find that the output of that model predicts people's behavior really well, just beautifully precisely. If you were to go out and collect data on people's intuitions in this game, it just matches the model really, really well. And it's actually not just linguistics. Across a wide variety of disciplines, people have just found empirically that models of recursive social reasoning under uncertainty predict people's behavior really, really well. Now, in my PhD, I've been lucky to get to work with people across actually all of these disciplines. And when I say work with, what I mean is sit next to and pair program models with. And over the years, I've come to the conclusion that people in many of these disciplines are writing code bases that actually look very, very similar. Their models all kind of share these common themes and common motifs. In fact, I have become persuaded that there's a whole programming paradigm lurking here, a paradigm that I've been calling the recursive rationality paradigm, where by rationality, what I really mean is being Bayesian in the face of uncertainty. And so it's not just a programming paradigm, it's a probabilistic programming paradigm. That's the good news. The bad news is, having spent, again, many years of my PhD sitting down and working with people across all of these disciplines, who, by the way, tend not to be professional programmers, they tend to be scientists by training, I've come to believe that programming in this paradigm is really hard. And I'd like to actually take a second to try to convince you of why programming in this paradigm is hard. I think programming in this paradigm is hard actually for the same reason programming in any paradigm is hard, which is correctness and efficiency. Here's the problem with correctness. The problem with correctness is that when you're thinking about people thinking recursively about other people, you invoke this rich vocabulary of words like believe, think, see, do, know, want, imagine. But when you're writing a probabilistic model or programming in a probabilistic programming language, the words you get to use are words like sample, infer, condition. So as programmers, you're constantly translating between believe, think, see, do, know, want, imagine, and sample, infer, condition. And who knows if the semantics are preserved. And if they're not, you end up with a whole bunch of really tricky, subtle bugs. Bugs like having one agent secretly have mind control over another agent in a way you didn't anticipate. That's the problem with correctness. The problem with efficiency is that when you have agents thinking recursively about each other, there's this combinatorial explosion in possible states of the world you have to keep track of. Not just possibilities of the real world, but imagined possibilities of imagined worlds, imagined by possible agents, imagined by other agents. You can see how this rapidly gets out of hand. And in fact, in practice, if you ask a cognitive scientist, they might tell you that running their model and fitting it to data might take not just minutes or hours, but actually days of compute. And I think that this is a fundamental roadblock to the progress of science in many disciplines. Because if you're a grad student and it takes you 3 days to test your hypothesis because it takes you 3 days to fit your model to data, then you think about science in a completely different way than if it takes you, let's say, 3 hours or 3 minutes or even 3 milliseconds to test your hypothesis. Okay, so over the past couple of years, I've been thinking about how to address these problems. And I've been trying to do that by building a new tool, a new programming language. And that language is called Memo. Memo is a domain-specific probabilistic programming language. And it's specialized for the domain of models of people thinking recursively about each other. And here's what Memo does for you. It addresses the problem with correctness by being designed not around the sampling of random variables like nearly every other probabilistic programming language on the market, but rather around agents who make choices. In Memo, you use words like believe, think, see, do, know, want, imagine, and the semantics of these constructs protect you from the kinds of bugs I was talking about before. As for efficiency, Memo realizes that when you're thinking about possible worlds, almost by the definition of possibility, these possible worlds are independent, and you should be able to compute over them in parallel. And so Memo compiles models to parallel array programs that can run really fast on modern hardware, like on GPUs. In fact, specifically, Memo compiles models to JAX. Okay, let me give you a little demo of how you would use Memo to build the model that I described for you at the beginning of this talk. The first thing to say is that Memo is embedded in Python. And so when you start writing Memo, you can just start writing Python, for example, to set up the rules of the game. In this game, there are 3 objects. Let's call those reference to borrow some jargon from linguistics. There's these 4 words you get to use. Let's call those utterances. And of course, we need to write down which utterances describe which reference. So for example, green describes the green square and the green circle, but not the pink circle. Okay, the next thing we have to do is say, well, what do we want to compute? So I told you that Memo computes arrays. The type of array we're interested in here is just like the data table from Ching and Franca that I showed you earlier. So we want an array that's the data table prediction of if a listener in this game heard some utterance U, then what's the distribution of reference that they're likely to guess? Okay, the next thing to do is to set up the recursive reasoning. Now, when I described this model to you, what did I say? I said there's a listener. The listener thinks there's a speaker. The speaker is given a referent to communicate, and then the speaker chooses an utterance with which to communicate it. Here's how you write that in Memo. You say there's a listener. The listener thinks there's a speaker. The speaker is given a referent, and the speaker chooses an utterance to communicate. You write this model the same way you would explain this model to like a friend at the bar. Okay, how does the speaker choose an utterance? Well, there's 3 factors that are important. The rules of the game, so the utterance must be denotationally consistent with the referent. There's recursion. The speaker thinks recursively about how the listener might be reasoning, and so notice the recursive call to the model L that we are currently building. And finally, rationality. The speaker chooses with a softmax over the probability that the listener guesses the correct referent. And notice, by the way, that these two terms introduce these new parameters, the number of levels of recursion and the softmax, or the temperature of the softmax. Okay, we're really close. Only two more things need to happen. First, the listener needs to observe what the speaker says. So this is kind of like conditioning. And the listener updates their belief. And finally, the listener makes a guess. They guess which reference the speaker actually meant. And finally, we compute a distribution, or a predicted distribution, over the listener's guesses. And that's it. That's the whole model. If we run this model at t equals 0 with no recursion, here's what it predicts. It generates a data table indexed by utterances and reference. And for example, this data table tells us that if the listener hears the word square, they're 100% likely to pick the green square. This was borne out by the experiment we did at the beginning of the talk. However, this model also predicts that if the listener hears the word green, they should be perfectly 50-50 between the green square and the green circle. And that's not quite right. That's not consistent with Ching and Franca's data. However, if we run this model with one recursive level of reasoning, so at t equals 1, it does predict a preference for the green circle over the green square. Now, let me compare this model with how you would write it before Memo, so using an ordinary probabilistic programming language. The code on the right is something I took verbatim from a computational linguistics textbook, and it's written in a probabilistic programming language called WebPeople. And let me make a few remarks about this. Firstly, I think that the Memo version matches our intuitive description about how we would talk about this model. It uses words like believe, think, see, do, know, want, imagine. It's about 10 times faster on the same CPU, and if you were to plug in a GPU, it would immediately start using that without needing to change any code. It's end-to-end differentiable, so you can optimize parameters like this at softmax temperature by gradient descent. Because it's all in Python, you can use the broader scientific Python ecosystem, like you can make plots with matplotlib, and because it's fast, you can even make these interactive plots that refresh live and really let you get a sense of how the parameters affect the predictions. And finally, it integrates with the broader JAX deep learning world because it compiles to JAX. We've implemented a lot of models in Memo, and each time we do so, we find that they're several orders of magnitude faster than the best implementations we can find online. And generally, you need to write dramatically less code in Memo than otherwise. Perhaps for this reason, Memo is used by a lot of labs around the world now, and several papers have been published that use Memo models inside them. Memo has also been used as a teaching tool in a lot of courses and textbooks and summer schools around the world. Maybe the thing I'm personally most jazzed about is that the cognitive science and philosophy of mind communities have been using Memo not only as a tool, but also as a way of thinking about what theory of mind even is. And over the past few months, I've written a number of papers that try to argue that ideas and motifs from programming language theory can actually be really useful for us to understand how minds think about other minds. And I'll just make a plug. If you want to hear a little bit more about this, you can come hear my talk at Onward tomorrow at 11, and I'll say a little bit more about that. One more slide. I wanted to end by saying that this paper that I just presented has the longest acknowledgement section that I've ever published in a paper. I'm the one up here giving this talk right now, but this project wouldn't have been possible without the help of actually dozens of people across dozens of fields and disciplines, and I wanted to extend my gratitude to them as well as to you for being here. Thank you.
Okay, any questions? So perhaps I have one question to get started with. So you mentioned that Memo is already being used in many places by a lot of people. What are the comments and what kind of feedback did you get so far?
Yeah, so on the whole, the feedback I get from Memo users is they're delighted that they can write the models in the way that's intuitive to them using the vocabulary that they're trained to use, and they're delighted that it runs a lot faster, and at the same time, they're kind of they're really excited about learning about array programming and JAX, and this whole world of like high performance computing and differentiable programming and probabilistic programming, like this isn't really very common in the community, and I think they just get very excited that these tools exist. And Memo is one thing you can make by putting these things together, but there's so much more. Like you can see their eyes light up with like all of the possibilities of things you can do. And so I don't know, I feel like there's a lot of scope for interesting things that can happen.
Okay, that's great.
Yeah.
So one more question?
Yeah, that was a very cool talk. I'm just curious what kind of experiments you've used to model your data using Memo. Do you have any practical examples where you've actually applied it yourself or other labs that you know that have used it?
Yeah. So as I said, a lot of people have written a lot of papers where they run experiments, like actual behavioral experiments. They'll ask real people, with IRB approval, some questions, and then they'll collect that data, and then they'll try to compare that data to outputs of models. I'll give you just one example of this that I personally find very moving. There's a team of psychiatrists at the University of Rochester who are really interested in the dynamics of teenage suicidal ideation. They're interested in how children or teenagers think about themselves and their parents and their therapists kind of recursively in the strategic way. And they just got an IRB and a grant to study this by collecting data in their clinic and comparing it to a Memo model that they wrote. So I find that work really inspiring and exciting.
Cool, thank you.
Okay, thank you again.
Very good talk.
All right, and so we are ready for the next talk by Paulo, and Paulo is going to tell us about DSL for robot software.
Thank you so much. So can you hear me in the back? Sounds good. So thank you so much for coming. My name is Paulo. I'm a PhD student at Carnegie Mellon University and University of Lisbon. And today I'll be talking a little bit about our domain-specific language for robot software. So in this talk, I'm going to talk about robots crashing, but more than robots crashing, it will be about preventing robots from crashing. So let me talk a little bit about myself. I come from a very small country called Portugal, and a few years ago we had this live demonstration on how not to throw a drone. But to be fair, this was like 12 to 13 years ago, and at the time building robot software was way more difficult than it is today, also because we have many new frameworks, being one of them the robot operating system. And so ROS is one of the most popular platforms for developing robotic systems because it focuses on component reuse. The idea is that you have this philosophy of modular tools-based software development where you have an ecosystem of off-the-shelf components. So before you had this idea of having a new drone, you had to write your software from scratch. Now you have a driver component that you can reuse. You can have object detection, navigation, robot localization, or even control capabilities in your software. And all you have to do is change the configurations on these components, and you have your system up and running. And so this idea behind ROS was actually pretty much popular, that today it's used very widely in many different industries from BMW, CAT, and Siemens. However, nothing is perfect on ROS land, right? So the lack of documentation in these components, and even when documentation is present, these are not enforced, lead to what we call misconfigurations. So these misconfigurations arise from mismatched expectations and guarantees that components have when we're trying to configure and integrate them. Let me give you one example. So again, ROS works on a communication model which is the most popular one is the publisher-subscriber model. On your left, you have, again, our driver that publishes our RGB images to a topic. And now on our right, we have our object detector that is expecting grayscale images of a kitten. Unfortunately, as you can see, there is a mismatch in terms of the image color expectations between the publisher and the subscriber for these components. And so your drone wouldn't have object detecting capabilities, it would crash. How great would it be to have some sort of specification on both ends of the communication to ensure that this doesn't happen even before running the system? So our idea is that by specifying these properties over the component's configuration and then in their integration, we can detect these misconfigurations prior to deployment. And this is where we introduced ROSpec. So ROSpec is a domain-specific language for refining ROS components, configurations, and their integration. And the main idea is that each one of these components should be accompanied by a specification file such that we can detect these gaps in the configuration and integration of the different components. So the design of the language is based on two main ideas. The first one is we based our design on this really amazing prior work by me. Where we analyzed like we analyzed like thousands of questions from Stack Overflow to try to understand what types of errors people make, and we have a taxonomy. And so we want our language to address real-world misconfigurations that developers make. The second idea is we have different stakeholders that develop these components and use these components. So on our left, we have all the Bobs who create these reusable packages and the components. They have to interact with source code, configuration files, XML files, YAML files. And so they create and make these components available. On our right side, we have Alice, who is responsible for taking all the different off-the-shelf components and integrate them together. And they often do this with these sort of configuration files. So ROSpec works on a different layer of abstraction where developers can add specifications to these components. I'll give you 3 examples for the interest of time. So again, on our left side, we have a component writer specification, those who write components and make available. And on our right side, we have the component integrator who takes these sort of specifications and instantiate them. So we use established, very popular PL concepts to add semantics to the configurations of our components. So the first ones are liquid types. So sometimes our configurations have meaning, and they are not just doubles. In this case, for example, max acceleration only allows positive max acceleration values. Another thing that we also have are dependencies between different parameters. So in this case, we have this height velocity limits flag that should be defined when we also define the max velocity. So we also add this notion of dependency between the types of the different parameters. So if max velocity is set, then height velocities also must be set. And so our language can give you a warning when this doesn't happen. Now, we also use liquid types with a twist. So usually, liquid types are used in the source code to refine the types of variables. In our case, we also use it to structurally refine architectures. So as you may remember, these components publish and subscribe to information. And in ROS, and in not just in ROS, but in overall component-based systems, sometimes we have restrictions at the architectural level where we're trying to refine the architecture. So in this case, there must only be one publisher to the topic. So when we have our component integrator trying to create 2 instances of this specific node, we can raise an error because we know that this specific restriction is not complied. So the final example I have for you is also in the sense of adding more semantic information. So ROS has this notion of policies that refine component connections by providing some sort of semantic information, like grayscale images or RGB images being published and subscribed, and in this case, quality of service policies. In this case, they allow you to refine the settings of the communication model between a publisher and a subscriber. For example, if a subscriber is expecting a reliable communication, there are some restrictions. So if the subscriber is expecting a reliable communication, the publisher cannot be like, meh, best effort, right? And so for all the settings, for all the different publisher subscribers, the developer must comply with all these different tables for ensuring that the communications are well connected. When they don't, they only find those, usually they only find those when executing the system. As you can imagine, figuring out the right QoS settings to use for nodes is a pain. There are certain combinations that are not compatible, so for every node, you have to check this table and make sure that all subscribers and all publishers agree with each other. This is a quote from a study from Open Robotics, from a user that pretty much fits what we're trying to detect here. And so with our language, the developers can pretty much define the instance of the quality of service setting, attach it to the communication model, and then we provide all the verification internally. Now, I've showed you like half of the features that we have. Our paper have many, many more. Let me walk you through how did we evaluate the language. So we evaluated ROSpec on 2 settings, a medium-sized robot system and a data set of real-world misconfigurations. So for the real-world medium-sized robot system, I present you the Neobotics MP400. You can see these often in Amazon warehouses where they are responsible for carrying loads between places. In our specific use case, it is responsible for walking around and checking the inventory, so it needs to follow a path, avoid dangerous areas, and respect speed limits. And it is composed by some of the most popular components it ROS, like, as we've seen, obstacle avoidance, navigation, speed limit. So we decided to specify this system as a way to provide, for us to get a holistic view of how the different language features interact with each other, and if we could effectively model a real-world system, because developers are using this for real systems. And so we specified 19 different components using both liquid types and dependent types. It was 500 lines of code, and we were pretty much successful. We even tried to manually introduce some misconfigurations, and we were able to detect them. It worked pretty much well. Our second way of evaluating our approach was using this data set of real-world misconfigurations. So we manually inspected 182 questions from our amazing prior work, and where for each one of these questions we checked, okay, what packages are they using, what components are they using, configurations, and what's the fix, so that when we provide the fix in the specification, our language should no longer raise an error. And so for all these questions, we checked what are the components, the documentation. We encoded hundreds of different specifications. And we also used, if you want to access we have our very own website where you can try the language online and their specification to try to specify these components and see if we could effectively detect them. And what we saw is that, well, okay, effectively the language was able to detect a big part of the specification. So out of 123 errors, we were able to detect 61. 26 were referred as documentation because we didn't have the system configuration, just what components they are used, so we couldn't even specify the system. But we did have a good use of liquid and dependent types. Now, this was a very brief overview because 12 minutes can only get you so far. But again, you can talk to me anytime after these talks or even on coffee break. And since I have like 15 seconds, I will just leave my very shameless advertisement on I'm finishing soon. So please, you can contact me. I have a lot of experience in empirical research, software engineering research, and programming languages. Thank you.
Thank you. Are there any questions? Okay, maybe just a quick question is, so these days there are quite a few languages using liquid types, and I presume, I'm not sure if you mentioned this on the slides, but I presume that this is an external DSL.
Yes.
At least you have like the syntax and all that. So have you considered at some point doing an embedded DSL, maybe as a simpler prototype?
That's a really good question. So the current versions of liquid types that are embedded are, for example, liquid Haskell, liquid Java, Flex for Rust. So something that happens in ROS is it's multi-language. So we have C++, in the same ecosystem we have C++, Python, XML files, YAML files. So it's very difficult to have just one specific language for example, for one kind of system when it's actually an whole ecosystem of many different languages. And that's also why we chose an external DSL, because it can abstract all the different types of projects that we have, all the different file configurations that we have.
Okay, okay, thank you. Once again.
Oh, okay.
Okay, so now we will have Sam telling us about probabilistic programming for the second time.
Thank you. Okay. Hi, I'm Sam. Oh my gosh, this is loud. So I'm Sam, and today I'm going to be presenting work with my co-authors, John Lee and Stephen Hulton, titled Multi-Language Probabilistic Programming. So Karthik gave you a small taste of probabilistic programming languages, and so in probabilistic programming languages, there's the semantics of our programs are inference, and there's a very large design space that inference promotes. There's a funny little feature about these probabilistic programming languages, which is that if we want to have a small addition to these languages, it can have a huge impact on inference performance. There's kind of this expressivity, tractability trade-off that happens where we want to write models that better represent real-world processes. But at the same time, the more we restrict these languages, the stronger the guarantees are that we can make for fast inference. So we're going to take a quick look at this restrictive probabilistic programming language called DICE. Now, DICE supports probabilistic conditioning, as you would expect. It's very good at handling complex discrete structures, and it gives us fast, exact answers. At the same time, if you want something like a uniform distribution or a Poisson distribution or even just like an unbounded loop, this is not the language for you. So let's take a quick look at these restrictions. So in this little case study, we're interested in the probability that a packet will traverse some probabilistic, some router network that's defined using a probabilistic routing protocol and reach some end node. So this is very straightforward to represent using DICE. And we'll take each node and we'll model it as a series of flip statements. And if the node returns false, then the packet will be dropped. So as I pointed out, this is straightforward in DICE. And under the hood, it's using something called knowledge compilation to compactly represent these distributions. But if we want to make this problem a little more realistic, and instead ask the question, given an unknown number of incoming packets, how many packets will arrive at our destination, then something funny happens. So here's a standard way to model this kind of probabilistic program. We're going to model the incoming number of unknown packets as a Poisson distribution, and then for each packet, we'll query the probability of a successful traversal, and we'll total that, or we'll sum those and return the total to get our random variable. Now, as I pointed out, DICE can't handle any of these features in this new function. But if we switch to a language like Pyro, then we're all clear. Unfortunately, though, we're going to lose the benefits of fast inference that DICE was providing for us when we went to write this network function. So what if we could use both languages? What if we could use Pyro for those continuous distributions and get access to these flexible, expressive primitives, and at the same time use DICE to model the network function and get the benefits of knowledge compilation? Now, that's a very sort of similar situation to something we already know about in PL. We already have low-level languages and high-level languages, and there's a rich body of research surrounding interoperation already. But there is not really a probabilistic analog when it comes to inference. So to address this, we come up with multi-language probabilistic programming. And our contributions are that we solve this challenge of interoperation between an exact and an approximate probabilistic programming language. We prove this sound by providing a high-level specification and showing that it is soundly refined by a low-level model that denotes the particular inference strategies. And we also provide a reference implementation to showcase this trade-off between sample efficiency and sample quality. In a nutshell, a multi-language might look like this. We might have two grammars where we have some perhaps typed language on one side of this multi-language and maybe an untyped language on this other side of the multi-language. And we'll take each grammar and we'll extend them with boundary expressions to perform this interoperation. And in our setting, we define DISC and CONT, where DISC is a discrete probabilistic programming language that performs exact inference, and CONT is a probabilistic programming language that performs approximate inference with sampling and has access to both discrete and also continuous random variables. So when we actually look at a distribution in FLIP, let's say, what we're going to do is we're going to compile this, this data structure called a binary decision diagram, or a BDD. And this, for all intents and purposes, you can just think of as a fancy data structure to precisely represent the distribution that we're interested in. Alternatively, if we're in Kant, we're going to sample distributions immediately. And so this flip statement will evaluate to either true or false. And we'll have to repeat this process many times and use a number of executions to approximate the semantics of our program. If we want to look at something slightly more complex, where we define two coins, x and y, and we're interested in the probability that y is true, given x or y being true. And so in disk, we'll return that BDD that represents y, but we'll also compile this thing called the accepting formula, which is constructed through the observe expressions and represents the conditional probability. In Kant, we will return weighted samples of y, where the weights are drawn from those observed statements, here returning 1 if x or y is true, or 0 if that is false. Now, both programs shown denote the probability that y is true, given x or y is true, and specifically the semantics of both programs is 1/2 in this case. So we want to perform sound interoperation, and to do this, we identify two invariants, namely sample consistency and also importance weighting. So here's a disk program where on line 1, we define some flip statement, some flip expression, and bind it to x. And then we access that free variable on line 2, alias it to y. And then again, we access that free variable x and can join it to y in the Kant language. So as I pointed out, disk produces distributions and Kant samples those distributions. So the first time we access that x, we'll either evaluate to true or false. But the second time we evaluate x, we better make sure that that is consistent with all previous statements. So in our boundaries, we need to ensure that this sampling effect only happens once so that this interoperation is correct. And we do this by conjoining an extra condition onto the accepting formula during interoperation. We also require this thing called importance weighting. So here's that same program that I showed you before. And the semantics of this program is 1/2. But what we've done is we've introduced more boundary expressions to sort of make this more exciting. On line 1, we're going to 1/2 of the time sample x to be true. And we'll produce this disk program. And the semantics of this program is that we're interested in the probability of y, which is 1/2 in this case. The other half of the time, we're going to sample x to be false. And here, the resulting program has the semantics of 1 because we're interested in the probability that y is true, given that y is true. It's always 1. So to actually use these results, we need to sample for some fixed number of times. Let's say that's 100. So perhaps 50%, or for 50 executions, we get 1/3. 50 executions, we get 1. And if we actually just take this naive expectation, we get the wrong answer. So what we really need is some kind of corrective factor here. And so we'll take the weighted expectation, where these weights are called importance weights. And we need to define a correct importance sampling or importance weighting scheme. So the importance weights come from these observe statements. Here, an observe of true corresponds to a weight of 1, and the observe of y corresponds to a weight of 1/3. And this gives us the answer we expect. So we also prove this sound. And we do this by defining a high-level model, which denotes the semantics of our programs without paying attention to the inference processes that we're operating over. Specifically, these are the ground truth semantics, and it's uniform over the multi-language. And then we also define a low-level model, which is the denotational semantics that capture the specific details of inference. We show that the high-level model is refined by the low-level model, and basically that important samplers defined in the high-level model are equivalent to ones defined in the low-level model. So if we take a look at that program from before, what that means is that the high-level semantics are going to take syntactic flip statements in both cont and disc, and those will denote semantic flip statements, and then observed statements will denote this semantic score. And this is operating under, this is a pretty standard thing to do, and this comes from the Staten et al. Paper in LIX 2016. And the semantic domain for all of this is a dist plus writer monad, where the writer is accumulating those importance weights. We also have this low-level model, and this is just building up the intuition, or like the denotation of those two inference strategies that I kind of touched on. These are also operating under the dist plus writer monad, and the disk, the denotation for the disk expressions will be knowledge compilation, and for the cont language, this will be likelihood weighting. And when we reach a boundary expression, we'll just switch over to the other low-level model. So we also provide a reference compiler and have evaluations. And so here's one of our two tables. Specifically, here we're evaluating that arrival model from the motivating example. We have some discrete Bayes nets, and we also include in this table an undirected gossip protocol as a probabilistic model, which is quite adversarial to knowledge compilation. We're interested in evaluating two metrics, sample quality, which is measured as L1 distance from a known solution, and sample efficiency, which is measured by the wall clock time for taking 1,000 samples. Our baseline is cont, which performs no interoperation. And what we do to define multi-people programs is we're trying to insert boundary expressions that will heuristically produce the highest quality samples while still being practical and efficient. And what we see is that inserting these boundaries allows for a trade-off between sample quality and time per sample. Yeah, I'm happy to take questions now.
Okay, any questions?
Hi, thank you for the talk. So in your experiments, how did you choose the boundaries between disk and cont, given some of the Bayesian nets were expressible in both the languages?
Mm-hmm.
So what were the heuristics behind those?
Yeah, we tried to just encapsulate as much of the discrete random variables in disk as possible, but obviously we can represent those discrete Bayes nets fully in disk, and evaluating 1,000 samples, reevaluating that program 1,000 times is inefficient, so there's like just a heuristic balance to make sure that that's within like a reasonable expectation of wall clock time.
So you kind of try to balance between the wall clock time and the accuracy?
Yes, yeah.
Oh, okay, thank you.
Okay. Maybe one last question while you switch.
Mm-hmm.
Cool. Thanks for a very interesting talk. So I was curious, so the way I'm used to thinking about interoperation between probabilistic programming languages is through the idea of like black box probabilistic programs, right? So having probabilistic programs, each of them guarantee that they satisfy a certain API or spec where you can either sample from it or evaluate the probability of a certain sample. And then as long as all languages satisfy the API, you can compose them through that lens. So I'm kind of curious with this like deeper language code level integration that your system allows, like what kinds of additional flexibility do you think it enables?
That's very interesting. I think we should probably talk about that offline. That's yeah.
All right, thanks.
Okay, let's thank the speaker again. Okay, so for the next talk, we are going to have a talk on polymorphic records for dynamic languages, and the presenter is Loic.
Yeah. Can you hear me okay? Right. So this is a joint work with BP Castagna, which is here in the room. This talk is going to be about type systems, and in particular type systems for dynamic languages. So think TypeScript. In our case, we are working with a team at Elixir to develop a static type system for that language. This is what motivates this work. So if you've seen the keynote of Christos Dimoulas on Tuesday, you might remember something like this. And basically, the point is to say that if you want to be able to type a program in JavaScript, for instance, you need a number of features. So you need set theoretic types, union, intersection, and even negation. You need subtyping, you need polymorphism, occurrence typing, and also gradual typing. In this talk, we will have all these features except gradual typing. We do have gradual typing in Elixir, but this is kind of orthogonal to what we do here. So in particular, to give you intuitions, we use unions to type branches, so like if, then, else, and these kind of things, and also occurrence typing. We use intersection to give overloaded types to functions. And we use negation to type, for instance, case expressions. So in this talk, what I will talk about is extending the type system that we have with a polymorphism which is specific to records. So our approach and the way in which the way in which it differs from TypeScript, for instance, is that we design type systems that are sound by design. So we have a theoretical framework that we call semantic subtyping, which will give us the tools to derive type systems that are well adapted to dynamic languages and programming idioms that we can find in such languages. So the problem is that, well, record types are really important in Elixir, for instance. And if you want to be able to type check the libraries using records, well, you cannot do it currently with the system we have. So we will need to extend it to support row polymorphism, which is the specific kind of polymorphism I was speaking about. So a quick example to show what row polymorphism is. So let's take this function here, which is written in an Elixir-like syntax. This function takes as input a record, which has a field called ID, which has an integer inside, and we just increment this field, the value of this field by 1. So if we want to give a type annotation to this, we will say, OK, I have a record as input, which we denote with the brackets. This record has a field ID of type int and can have any other field. This fact that it can have any other field, I indicate it with these 2 dots here. This is what we call an open record, if you're familiar with it. The output type is going to be the same thing. So now the problem with that is pretty well known, is that if I define a record with more field than just ID, I can apply my function. But then what happens is that this argument here has this type with the 3 fields. And then I can type check the application here because this type is going to be put in correspondence with this one, and we agree on the type of ID, and we agree that there are other fields, but I don't know which one they are. So in the end, my output type, so the type of this element here, is going to be this thing exactly. And then this thing exactly is something that tells me that ID has a type int, but tell me that I have arbitrary other fields, but I don't know what thing they are anymore. I forgot what they are, so I lost some information. So in the end, if I want to use another field from this record, I cannot do it because type checking will fail. So the solution to that also is well known. The idea is to replace these arbitrary other fields by a variable, and this variable just gives a name to the other fields. So I can say what I had at the start is exactly the same thing as what I have at the end. So when I apply my record, what will happen is that I will be able to find an instantiation of the variable to these 2 other fields here, which then, if I look at my function under this instantiation, tells me that, OK, I remember that I had some other fields, and they are these ones. So I can apply my projection. So this is the idea of polymorphism, and this is like a really old thing. So there's nothing new here. So what makes it difficult is that in our framework, as you saw in the first slides, is that we have a lot of different features. In particular, we have these set theoretic types, union, intersection, and negation. And we have this semantic subtyping. So semantic subtyping is not just the name of our framework. It's also what kind of subtyping we use. And it is a subtyping that is not syntactic, but that is defined through an interpretation of the types. Remember also that our framework already has parametric type polymorphism. So the idea will be to extend the tools that we have already for type polymorphism to row polymorphism. So if I go back to my example, what do I need concretely to be able to type check it? So this is just to remind the types of the function I have and my argument. And now when I want to apply this function to this argument, the thing that I need to check is this subtyping constraint, verifying that the type of the argument is a subtype of the input type of the function. So there are two things needed for this. One thing is to define exactly how to decide subtyping. And the second thing is to be able to find the correct instantiation of the variable row. So first thing, subtyping, how to decide it. And I will start by describing really quickly what semantic subtyping is, what the core idea of it is. And the idea is to consider an interpretation of type in which intuitively the interpretation of a type is the set of the values it contains. So integers will be interpreted as the set of all integers, strings as the set of all strings. And then the really nice thing is that we will interpret set connectives on types as the corresponding set connectives on sets. So union on types is interpreted as union on sets, and so on. So this gives a really intuitive understanding of set connectives on the types. And then my subtyping is going to be defined through this interpretation by saying that a type T is a subtype of a type S if the interpretation of T is contained in the interpretation of S. Right, so to say it again, I start from my interpretation of type, where I find out what formula I need to decide containment of one interpretation inside another. This formula, I lift it to the level of types. So I get a formula that tells me on types when a type is a subtype of another one. And this formula, we can actually refine it into a backtrack tree algorithm to decide subtyping. And here, just one thing I want to say. So I don't want you to understand this. I just want to point out this thing in red here, which surprisingly is the only difference we have between the subtyping algorithm without row variables and with row variables. So adding row variables to our system, just in the end, asks just to add a little check in this algorithm. And this is just checking that the row variable we consider is contained into a finite set. So this is interesting because it means that from the point of view of asymptotic complexity, having row variables or not having them is the same for the subtyping algorithm. So yeah, to type check our example, first thing was deciding subtyping. Second thing is to find a correct substitution for our variables. So this is the unification problem. In our case, we call it tallying problem because we don't have equality constraints, but subtyping constraints. So once again, the idea is going to be to extend the algorithm that already exists for type variables and extend it to row variables. One insight I could give on this is that one important step of unification or tallying is to decompose constraints into smaller subconstraints. And for this, we use a generalization of the subtyping formula that once again have been, well, we found it by looking at the interpretation of types and bringing it back to the level of types afterwards. So this algorithm is sound. This is good. It is not complete. This is less good. But OK, one thing is that if you forget about set connectives, we are conservative with respect to the usual algorithm of polymorphism. So without set connectives, we are complete. Now, why aren't we complete overall? The thing is, we want to be really precise. For instance, if we look again at our function bump ID here, its type is basically the type of the identity function, right? So if I give it as an argument a type which is a union type, well, I want to get the same type as a return. And this is indeed what our algorithm does. It gives us the union type as a return type for this function. But if we will consider a less general or weaker algorithm that we would hope to be complete, we would rather get something like this, where the union will be smashed. I mean, the union of record will be smashed into a record of unions. And in particular, we lose a lot of precision because you can see, for instance, that the correlation between having an integer here for the tag and having the field com present is lost in this final record. So what I presented before was an extension of the framework of semantic subtyping and an extension of the tools we can have by working on types. So we have a unification algorithm, or tiling, and we have subtyping, and also we have an interpretation of types. But what I showed was independent of the language you could choose. So now what I'm going to do is to define a language and give a type system, and this type system is going to be using semantic subtypings and set theoretic types and row polymorphism. Once again, you don't need to look at the details, but we define a type system. We define a lambda calculus which has records, and it has record extension. It has deletion of fields on records, and it has projection of fields. And we can show that this type system has preservation and progress. Since it is non-algorithmic, we define an algorithmic type system. So you can notice, for instance, in the application rule, how we need to find a correct substitution to relate the type of the argument to the input type of a function. So this is given by the tiling algorithm. And of course, this algorithmic type system is sound and complete with respect to the first one. So to summarize, what we have shown in this work is that the row polymorphism, row polymorphism, which has been around for a long time, is not limited to syntactic approaches to subtyping, but that we can also integrate it into the semantic subtyping frameworks with set theoretic types, and that it actually fits pretty well because we can extend existing algorithms with row polymorphism. And so this is really important for us because there are several implementations. Thank you very much. There are several implementations of semantic subtypings and set theoretic types in the wild. And it's really important for us that developers can just extend what exists with row polymorphism. On the side of implementation, to finish quickly, this is work in progress to implement it in our language, our research language, which is called Sidious. And then once it's done, we would like to implement it inside the type system for Elixir. So I will stop here. Thank you very much for your attention.
Okay, maybe time for one quick question.
Hi, thank you for your talk. Just out of curiosity, and since I think row polymorphism can easily support recursive types, especially equal recursive types, is there, after integrated into the semantic subtyping framework, is this kind of easily supported recursive type would it still work?
So we have actually, I didn't speak about it, but we have recursive types. We work with recursive types already.
Yes, so it still works after you integrate into the semantic type subtyping framework.
Yeah. 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 I don't know if it's your question, but yeah, we have recursive types. We only work with recursive types.
Yeah. Thank you.
Okay. Yeah.
Okay, let's thank the speaker.